use the raised hand function so that we can help moderate the discussion and let everyone have a chance to talk. Does anyone have comments or thoughts after our discussion yesterday? Oh, and Marisa, maybe you're right. Is maybe Donica's not coming today? In which case,
was it me who's going to moderate today, Will?
I don't know. I just thought she said she switched with whoever was doing it tomorrow.
Oh, so are you moderating, Dave?
Yeah, I kind of feel like maybe that's what we decided.
Sorry, I got confused. I thought it was Thursday that she was unavailable, but
yeah.
But given that she's not here, it must be, and she must have the conflict today, and so.
Yeah.
Yeah. Well, according to your email today, it's Dave and
Sorry.
It's Dave and Charlie today.
Dave and Charlie. All right. Awesome. Well, good. That makes me feel better.
Yeah, so maybe we should just go ahead and get started. What do you think, Will?
Yeah, that sounds good to me.
Okay, so I think first up, I don't have the schedule in front of me, but I do remember that Hydron is the first speaker. So Hydron, why don't you go ahead and share your screen and get started, 12 minutes. And yeah, I will probably jump in if it's starting to look long. And if you run out of time, we'll just have to skip questions for you or anyone.
Yes. All right. So I have actually no idea what you were seeing. Do you see the presentation in full screen?
That looks good. Perfect.
Okay, cool. Thank you. So yes, we've heard a lot about sensitivity of CLM actually yesterday in terms of internal parameter testing and estimation through large-scale experiments. I'm going to go a step back and tell you about a rather small sensitivity study that we've done with external parameters. And what we were interested in was the sensitivity of permafrost representation mainly to land surface parameters and initialization in a regional Arctic climate model. So I'll try to give you a very brief motivation of why we've been doing this. Okay, so we already know that permafrost in our model is sensitive to the parameters that we've just listed. So to the soil parameters that we put in, to the vegetation, to the initialization. Why do we need a sensitivity study? So there are scientific answers to this. We want to quantify the sensitivities to different parameters that we find for permafrost and also for our atmospheric variables. And we want to assess the impact that those parameters actually have on the quality of the representation of the atmosphere and the permafrost. There also is a, let's say, more honest answer, because we already have a setup of the model that works pretty well. And like one of the maxims is never change a running system, right? So why do we want to change our parameters anyhow? We need to shift our model setup to a very high resolution and a new model domain. So we need to change parameters anyway. And we would like to know where we have to be careful in the selection of the new parameters. So that's like the more honest answer to the above question of why we need the sensitivity study. So the setup, again, very briefly, we use a regional climate model that is composed of an atmospheric component and the CLM. The horizontal resolution at the moment is 25 kilometers for both CLM and the atmosphere. And the simulations that I am going to show you here are driven with ERA5 reanalysis data, and they cover 1979 to 2019. The forcing is at the lower and lateral boundaries. That actually means that we only have like a stop ocean, and sea surface temperature and sea ice are prescribed from the reanalysis data, and they are identical in all simulations. And the picture on the top of the slide just roughly shows you the domain. So there is yeah, can you see my pointer? Yes. Okay.
Yes.
So yes, so roughly the domain is the area north of 60 degrees north. You have Greenland and Iceland on the lower boundary, and then there's Siberia, and then there's the Western Arctic. And the simulations that I'm going to show you, they differ in vegetation, soil, and initialization. So there's a control run that runs with MODIS-derived plant functional types and a soil map that is derived from the FAO soil map of the world. And the spin-up was done for the year 1979. Then there is a run that is called PFT-ESA, where the vegetation is derived from an ESA product, from the ESA CCI plus land cover product. And soil and initialization are the same as in the control run. Then we've initialized instead of with 1979 with the year 2018, so warmer initialization. That run is called INI 2018. And then we have colleagues from the University of Oslo who have tried to come up with a different type of soil map for the Pan-Arctic domain. And that run is called MinSoil OBU, after one of my collaborators. So just very briefly, the differences that actually the runs exhibit. So this is the PFT-ESA example. The pictures show you the dominant plant functional type for each grid cell. For the standard setup with the MODIS-derived plant functional types, and for the ESA setup here. And you can see that there are rather impressive shifts in dominant PFT. So while in the MODIS setup, the dominant PFT throughout large parts of our domain are shrubs, this is changed in the ESA. So there's a larger part where the dominant PFT is bare ground, and then in other areas, trees are more dominant. This looks more extreme than it actually is. Because it's only the dominant PFT that is shown, and likely the changes that you see are just a switch in dominant PFTs. Then for the initial soil, there is on the left, there is a picture of the 20 centimeter soil temperature from the initial state of 1979, just to give you an idea what it looks like. And then there's the difference. So the initial state for the INI 2018 run minus the initial state of the INI 1979 run. And you can see that there are areas where the run is a lot warmer, and also areas where it's colder, and the impact is quite significant. So the color scale goes from -8 to 8 Kelvin. So the differences are quite big. And the last one is the soil. So this is just to make something that we can look at. This is the mean column percentage of sand in the model. And so the FAO soil map is, due to the way it was designed, a mixture of different maps, which is rather clear in the structure, and they don't obviously follow like geographic features, for example. While if you look at the soil map that the colleagues from University of Oslo came up with, you can, for example, see specific areas where there are mountain ranges, and it looks a little more natural and not as, I'd say, sketchy as the FAO map. I'm not saying either one is better than the other. They were derived in completely different ways, and they lead to differences in the model in the end. So very briefly, for the assessment of model performance, I am using station data and also data from the ESA CCI Plus program. So there is the meteorological station data that you can see here. Obviously, there is all the data are biased towards land because there are no stations over water. And for the soil temperature stations, you can see they are even more biased because they are only in like at least somewhat accessible areas, and there are not very many of them. So that's why we also use the satellite-derived products for permafrost. And here's an example for active layer thickness from the CCI Plus permafrost product. So results. What you see here in the first step is the sensitivity of soil temperatures that we find in our runs for 3 different depths. It's maximum annual ground temperature, actually. So it's in 20 centimeter, 36 centimeter, and 100 centimeter depth. And the dotted areas are areas where the differences were found statistically significant. I just want to point out the differences are small. So they're within -1 to 1 Kelvin. All the runs showed that the differences are rather consistent with depth. So like, for example, this area, this warm area here we can find it in all the depths. And the strongest impact comes from the changes in the soil parameterizations, maybe not so surprising. The changes in PFT actually mostly result in changes over perennially frozen ground. So it's mostly like in the areas of European Russia where we see big differences. And the changes in initial state seem to be affecting discontinuous permafrost mostly. This translates into changes in active layer thickness, of course. So in the top row, you see active layer thickness from all the runs. And then in the bottom row, there are the differences in respect to the control simulation. And then on the very right-hand side, I'm showing the CCI product, just to give you an idea of what active layer depth maybe should look like. Actually, if you look at them, there are differences. Like I said, maximum annual ground temperature changes translate into active layer thickness changes. But if you compare it to the satellite-derived product, they are all not looking very good. So there are obviously issues in all of the simulations still with respect to active layer thickness. Yes, so I've tried to quantify the representation of soil temperature. This is a very simple measure that you're looking at here. So you have all the different months, and then you have the different simulations. And the numbers are actually the bias between the station observations and the model. And you can see that there is a clear seasonal dependence of the bias. So the biases are somewhat smaller in the cold season, somewhat more pronounced in the warm season. They are all negative. And in terms of model representation, we see that shifting to the ESA PFT seems to improve the model performance in comparison to control. And the mineral soil changes actually seem to decrease the model performance in comparison to the control run. I just want to point out that bias is a rather simple measure for model performance, right? So in the end, we need to look at other measures, and we need to look at stuff like variability and trends that I haven't looked into so far. And if we look into the atmosphere, I've only taken 2 variables here, 2-meter air temperature in the top row and mean sea level pressure in the bottom row. And it's only summertime because all in all, the impacts on the atmosphere were rather small and mostly, or on atmospheric mean state were rather small and mostly not statistically significant. So the only, in terms of 2-meter air temperature, the only areas with statistically significant differences, for example, for the changes in the plant functional types are located here over Western and Central Siberia. And then we see that for the changes in the mineral soil, we have small areas with statistically significant differences. And so the PFT changes lead to direct feedbacks to the atmosphere that then change air temperature. And the areas where the maximum annual ground temperature were affected the strongest in the mineral soil experiment then translate into local temperature changes. And that happens through changes of the surface energy balance. So if you look into the fluxes, you can clearly see how this how this translates into temperature changes. And then we see in mean sea level pressure that mostly the impacts are small and remote. So the differences are not local over the areas where the temperature changes, but they are over the ocean. And so for a more detailed analysis here, it would be good to look into the changes actually in cyclone activity, but I haven't gotten around to doing that so far. So we can also look at the representation of the atmosphere in terms of the bias in 2-meter air temperature. So the structure of the table is the same here. You have the months, and then you have the different runs, and the color coding is the size of the bias. And actually, they're all pretty much the same. So there is no apparent impact on mean 2-meter air temperature representation from any of the changes that we've made. We can say one run is better than the other one. But again, bias is a simple measure. So we might have to look into other measures, especially into variability, to really assess if there are differences or if the runs are just all the same. Yeah, so basically, that was all I wanted to show you. We've tried to quantify the sensitivities of permafrost and atmosphere to our different parameters. And we found that with respect to physical representation of permafrost, the soil parameters are the most important parameters that change something, which is, I guess, not very surprising. And we've seen that vegetation impacts both permafrost and air temperature, and that the remote impact on the mean state of the atmosphere are small and mostly not statistically significant, but that might need further investigation as well. And then impact of on the representation, so on the model performance for our atmospheric variables and permafrost, we've seen that changing the mineral soil component in the model actually decreases the model performance in comparison to the soil temperature measurements that we've had. And the model performance with regard to air temperature was largely unaffected by the things that we have changed in the soil. So I'm open for questions and for remarks, discussions.
I think we went through the 15 minutes, so we should probably move on to the next presentation. But I will say that, and especially with these shorter presentations, this is the benefit of this online forum, is that there's already a bunch of questions for you, Hadron, in the chat. So, and I have some questions. If anyone else has questions, I think we should definitely be using that chat feature to try to get a bit more out of each one of these presentations. So I propose that we move on. We may, if we don't go over, have a little bit of time at the end to circle back to some questions in person. So the next speaker is Dev, and you'll have to give us your full name. I know you as Dev, probably most people do, but yeah, please go ahead.
Yeah, thanks. You see my screen? Hello, is that fine? Do you see the screen? Full screen? Okay. Yeah, thanks. Yeah, hi everyone. Yeah, for some of you who don't know me, so yeah, my full name is actually Devaraju. I'm working at the Department of Geosciences, University of Oslo in Norway. Yeah, today I'll present the plan for modeling the lateral flow of dissolved organic matter in CLM. Okay, yeah, some definition of the dissolved organic matter and some numbers to give a context. And dissolved organic matter is defined as the organic matter fraction in a solution that passes through a 0.45 micrometer filter. And dissolved organic matter is often quantified by its carbon content and referred as dissolved organic carbon. And so since the high latitude soil carbon reservoir may amount to nearly 1,600 petagram of carbon, the yearly lateral flux of carbon from soils to running waters may amount to about a fifth of net ecosystem carbon exchange. And the recent global estimates of the terrestrial carbon inputs to inland waters is about 5.1 petagram of carbon per year with large uncertainty. I mean, in the recent decades, the importance of dissolved organic matter in the carbon budget quantification has been recognized. And yeah, so the dissolved organic matter, which mainly originates from the vegetation, which goes to the rivers, and then ultimately it reaches to the oceans. And so far, only global land models like ArcGIS and JULES have the representation of dissolved organic carbon. Okay, and why why we want to represent in CLM dissolved organic matter? Actually, so in Norway we use NAR-ESM. In NAR-ESM, the CLM as the land surface model. And yeah, we want to make use of this land surface model and implement the dissolved organic matter and try to understand the link, dissolved organic matter link with the ocean waters. And that is especially important for Norway. And I'm sorry. Yeah, this is potentially for chord spanning. If you see this figure top right, this is the Secchi disk depth, which shows from 1900 to present day. Or in the Baltic Sea, the Secchi depth has declined. That means the visibility of the coastal ocean waters has declined. So that means, yeah, basically it's coastal waters are becoming darker, and and there are studies that try to link this darkening and then the climate warming. So there is a climate warming and also the chord spanning delays. If we see that from around 1870 to 1980, there is a delay of about 40 days, the spanning time of chords. And then there is again the reversal. So we basically want to understand the link between the DOC and this chord spanning time ultimately. We have a project called Green Blue Project, which is funded by Norwegian Research Council. This project mainly aims to understand the terrestrial ecosystem change impact on marine ecology. And how we want to model is that is make use of the river routing model like Mozart in CLM. So as I said, in NAR-ESM, NAR-ESM uses CLM as its land model. And so we mainly want to couple the soil biogeochemistry model of CLM with the Mozart and solve the mass balance equation for dissolved organic matter transport. So this is the main idea, is like combine the biogeochemistry with the Mozart and to estimate or quantify the discharge of dissolved organic matter to oceans actually. So our long-term plan is to couple the land model to this DOM discharge to the oceans and see in a full coupled model how that can, DOM impacts on the climate or like energy budget changes. So for the moment, I plan to implement the mass balance equation for DOC as shown here. Maybe in the beginning, I'll make the reaction term 0, kind of assuming it as a tracer first, and then maybe gradually improve that. Yeah, this is a kind of a detailed schematic of dissolved organic matter input and the transformation and losses. Here are the inputs I listed from 1 to 6. That is, this is the input that is mainly like through fall from the canopy exudation and the rainfall, and remaining all like soil processes like root exudation, microbial analysis, humification, and other processes in the soil which produce the dissolved organic matter. And the output is like mainly the lateral flow which goes to the rivers. So I think I highlighted here in the blue. So lateral flow and the leaching, which is 11, may go TYM. So for initially I plan to consider only these processes highlighted in blue letters. And I think this is the true fall input for the equation, like the wet deposition, atmospheric deposition, which is like from the observations there are in the literature. It is I mean, there are estimates that 3 milligram of carbon per liter of the wet deposition, and the dry deposition is kind of a function of leaf biomass. But for the moment, I think we decided to drop out this, but we consider only the dissolved organic, carbon production in soils, which is given by this equation, which is based on the first order kinetics. Basically DOC production is a function of soil organic carbon, and the DOC production rate, you have the rate modifier depending on modifiers due to moisture and temperature. And this is vegetation. I think in joules, they do soil organic carbon pool is treated as a single box down to 3 meters, so without any representation of vertical distribution, and hence they consider this weighting factor actually, and also the dependency on PFTs. So maybe we may not need to consider this for CLM. Right. So this is the mainly DOC production, and we plan to draw up this DOC into the runoff, like both for the surface and subsurface runoff, by summing up all the soil layers if we estimate the DOC production in each soil layers. And also the most of dissolved organic carbon reside in top 4.5 centimeter of soils. So that's the equation for the DOC production. And then we also plan to include the vertical transport of DOC by considering the convection diffusion equation, and maybe also include the net change in DOC into the carbon cycle, soil carbon cycle equation. And that's the plan of what I am thinking to implement in CLM. And by then in parallel, we have decided to evaluate the runoff actually. So how well the CLM simulated the runoff or in the Phenoscandia. This is the, I just performed like 10 years simulation from 1950 to 1960, but I have here the annual 5-year, I have just considered the 5-year annual mean of runoff here. Compared with observation-based gridded data set. This is like called ERUN or Europe, and also this is from the GRDC database, Global Rivers and Dams database set. So, and overall, it seems the CLM is simulating pretty well. And if I just compare, this is actually rainfall, this panel, GSWP3 forcing data I have used, and this is the rainfall. So you see that the most of the rainfall, which is in the east, like west coast of Norway, is going as a runoff. And there are biases actually. If you see, this is the difference between the CLM and this is in one data set and the another data set. And yeah, this is the time series, the runoff versus the time, like monthly means, just. And this is only the blue, blue curve is for the observation based data set for the average over Phenoscandia. I mean, yeah, on average, CLM simulates pretty well, you could say. But on the annual means, if we see that the peaks are like somewhat in some years they're not matching. And if I see the climatology, in April, May, June, it is the underestimated the CLM, the runoff. And yeah, so this is just I wanted to check if how it follows, the runoff follows with the precipitation. And also, I just wanted to note that the peak actually is kind of shifting I think here in CLM. So this is kind of a preliminary just analysis. So we plan to, evaluate thoroughly. Actually. And yeah, I looked at for some of the regimes over Phenoscandia, 3 months with the highest average runoff belong to the spring, early summer, like typically from May to July. This is the figure. We see that this is the y-axis is for the E-run observational data set, and the x-axis is CLM simulated runoff. So the R square is like about 0.73, means, yeah. So for the dominant snowmelt high water, CLM simulates pretty well. But whereas for the dominant low flow runoff, the correlation is really like 0.16, does not simulate. So basically in the winter thing. So yeah. That is, yeah, from February to March actually. So this is it's really, it's not simulated well. And for resin, yeah, this is same again for the resin 3, like a dominant rain high water for this H3. So I call it. Yeah, only few grid cells, and it simulates pretty well. But whereas for dominant summer low water, again the the correlation is really like 0.4. And yeah, we try to look at also over catchments, river, like this is one in Glomma River Basin on Norway. So the blue, this is the river discharge data. Blue curve, yeah. Sorry.
If you just try to wrap up, okay?
Yeah, it's the last slide, I think. So from the GRDC, yeah, blue is the GRDC station data set, and the CLM simulated, CLM BGC simulation is the orange one. So if we see over catchment scales, I think on average, the CLM simulates higher values. I think, yeah, so yeah, we trying to look at more some more catchments and try to evaluate in parallel this runoff and discharge. I think that's all I have. Thanks.
Great, thank you, Dev. I think we don't have time for questions, but there are a couple of questions in the chat for you already, Dev. So please address those. And yeah, I think related to the complex topography in that region is definitely a challenge, I think, over Norway. So that's going to be an issue going forward. Okay, so our next presentation is by Ina van der Kellen, talking about global reservoirs. So Ina, go ahead.
Yes, so if everything goes well, you can see my presentation. So yeah, good morning. I'm Ina from the University of Brussels in Belgium. Yeah, and I will present my ongoing PhD work on reservoir implementation in CTSM. And this is together with my co-authors, and from NCAR, these are Dave, Bill, Martin, and Naoki. And so here you see a satellite image of a river, and in 2011, a dam was constructed on this river, and this led to the inundation of the upstream area and the creation of a reservoir. Now, the constructed dam not only regulated the flow, but also due to the water inundation, the surface properties were changed, altering the albedo, surface roughness, and therefore this reservoir is likely to impact the interactions between land and atmosphere. This is not only important on a local scale, but also on a global scale. Since the 20th century, humans have been building more than 45,000 dams worldwide, and this led to a very steep increase in reservoir capacity, especially from the 1950s onwards. And altogether, this led to a creation of open water surfaces, making up about 9% of global lake area. Thereby, the water retained on land does not only lead to a decrease in sea level, but also to a redistribution of heat from ocean to land. And this redistribution of heat contained in the water of the reservoirs is about 10 times larger than the heat uptake by natural waters, rivers, and reservoirs due to warming waters as a consequence of climate change. And this water is interacting with the climate system, but actually very little is known about this interaction. And so therefore, the main question of our study is, what is the impact of global reservoir expansion on the global climate? And to answer this question, we represented reservoir expansion in CTSM, and we performed transient, land-only, and AMIP-style experiments. But first things first, in CTSM reservoirs, we simulate reservoirs as lakes. And so in each grid cell, the lake column has constant water depth in time, but then this water depth varies in space. And the difference in precipitation and evaporation from the lake column are compensated by a runoff term, which can be both positive and negative. The mass of the lake water cannot change this. And to simulate reservoir expansion, we let the lake land units grow dynamically based on prescribed values at the start of the year. And this changes the water and heat content of the grid cell itself. And this is corrected for using energy and water correction fluxes to or from the atmosphere. This is runoff for water, runoff to the river for water, and sensible heat to and from the atmosphere for energy. So in this way, water and heat are conserved, and this is actually very similar to the changes, to transitions in crop and vegetation, which were already existent in the model. But these correction fluxes for lakes can become very large compared to their physical, to the physical fluxes, as we need to take into account the differences in energy of the lake water itself as well. So to minimize these artificial fluxes, we implemented a baseline approach where we use the reference states, spun up states, called baselines, to subtract at the start of the simulation in order to that when we are calculating the correction fluxes, only the changes compared to this baseline state are accounted for, and these correction fluxes are minimized. So this work is already implemented in the main branch of CTSM, and I've done it. We've worked together on this with Bill Sachs, and a similar method is used for glacier changes. And so we prescribe reservoir area fraction per grid cell based on the global reservoir and dam database. And we let the reservoir appear in its year of construction. And so to be consistent with this data set, we also updated the lake mask, which was originally for MODIS, to a new lake mask based on hydro lakes. This is not yet implemented. There is some changes needed in the mixer.tool to make this standard procedure. And so here you see the location of some large reservoirs in northeastern Canada and in Siberia, but also some individual reservoirs like Lake Nasser, Lake Volta in Ghana, and then some smaller dams around. And so then we performed land-only experiments where we drove CTSM by GSWP3 in SP mode. We conducted one with transient reservoirs and one without, with transient land use without reservoirs for the 20th century. And we see an increase in terrestrial water storage by the construction of reservoirs, which follows the increase in reservoir capacity. And this signal gets larger for grid cells with larger reservoir area fractions. And so here I show the mean change in terrestrial water storage over reservoir grid cells. And so we see the same pattern for other variables as well. For example, for albedo, we see a decrease as darker water surfaces are less reflective. And this is again more outspoken for larger reservoirs. Similar story for the latent heat flux, an increase of more water available to evaporate leads to increase in latent heat flux and a decrease in sensible heat flux, although not fully compensating this. To look at the feedbacks between reservoir and atmosphere, we ran coupled experiments with CESM AMIP style, 35 years with constant land use. So we had 5 ensemble members with reservoirs and then 5 ensemble members without reservoirs. And here I show the maps, only the grid cells which are statistically significant. And so here you see already that the impacts of reservoirs on latent heat flux in this case are overall small, but at some locations there is some large impact, and it's mainly the reservoir grid cells, no surprise there. So we looked at responses in the energy balance related variables, as responses in precipitation and moisture related variables were not detectable from natural variability. And so here I show the effect of reservoirs on the diurnal temperature range. They dampen the diurnal temperature range up to 1.5 degrees, again, very localized in reservoir grid cells. And on seasonal timescales, we see that this largest decrease happens during the summer month and is again largest for the largest reservoir grid cells. Then we looked at temperature extremes. So here we see that on the minimum nighttime temperature, as reservoirs have again a very localized decreasing effect. And this is most pronounced in summer and extends into the fall months. And then we also looked at maximum daytime temperatures. So there we see a decrease, cooling, and this is most pronounced during summer. And to explain these seasonal patterns of dampening a bit more, we looked at the different terms. We looked at the different terms of the surface energy balance. So here you see the subsurface heat flux, including light transmission through the lake water. And we see a very distinct seasonal cycle with during spring and summer months heat uptake. And then the heat is again released from September onwards. And this results in an annual almost zero net effect. And these patterns makes then the energy available in autumn, in fall months to evaporate, to increase the latent heat fluxes. And then sensible heat flux is decreased throughout the year. And this could be related to a decrease in roughness length, reducing the turbulence. And then we can also look at changes in the radiative fluxes. There we see that the course in net shortwave radiation can be explained by the seasonal cycle of albedo, where from June onwards we have a negative albedo from darker surface. And in the first part of the year, we see a positive albedo, which can be explained by the ice formation on reservoirs, leading to brighter surface than the surrounding vegetation. Now, small note here on the seasonal cycles. These are based on global averages, but you see a very clear northern hemisphere signature, which is a direct consequence of the fact that there are more reservoirs in the northern hemisphere. We also tried to take hemispheric bands, but that didn't really brought a lot of results. So this brings me to the main takeaways. So we included reservoir expansion in CTSM with dynamical lake area. We saw through our experiments that reservoirs dampen the daily and seasonal temperature cycle and temperature extremes, and this is especially the case in summer and fall. But overall, the global effect of reservoirs on the climate is small, but very localized to reservoir grid cells, and it can be substantial where reservoirs make up a large fraction of the grid cells. And then to end the presentation, I want to share the next step in my PhD project. So we are taking the next step towards a coupled representations of reservoirs in CLM, and this is to include the another important effect of reservoirs being the regulation of river flow. And so to this end, we're collaborating with Martin and Naoki and Sherwin Garari to implement a reservoir parameterization in Mesorouter, the routing model. And so we're using a reservoir parameterization, which is widely used in global hydrological models, aiming to decrease the intra-annual and intra-annual variability of reservoirs, and also takes into account irrigation demands on reservoir. And this is then work which nicely lines up with the work which Eric and Naoki are working on, being the coupling of Mesorouter and CLM to communicate outflow and irrigation demands. And then at the very end of the road, the idea would be to have a closing irrigation cycle, water cycle. And on this note, I would like to thank you, and I hope there's still time for questions. Otherwise, you can ask them in the chat.
Yes, great. Thank you, Ina. That was excellent. Yes, we do have time for questions. So please raise your hand. And there's also some questions in the chat, and I'll let Charlie handle this. If anyone has a question, please raise your hand. Or we can read one of the questions that's in the chat.
Yeah, maybe I'll start with the chat ones. Peter Lawrence asks about drying up lakes like the Aral Sea, Lake Chad, and Lake Eyre in Australia. Is that something you're planning to look at as well?
Currently, that's not included through the models. In theory, the code should be able, the dynamical lake code should be able to handle decreases in lake area too. But there is currently we have no good data sets to describe these changes in lake area fraction, although there's been made progress on this satellite-derived products. But right now, I don't have really plans in that direction. But it should be possible with our changes.
Cool. And then Stephanie Falk asks if you take into account the reduction of water downstream of dams.
Right now, this is not in the model, as we only look at the grid cells. But this is work, coming work. So on the and we will look at the reservoir parameterization on stream flow in the routing model. And then,
Marisa asks if you have been looking at the effect of the temperature of the water flowing into reservoirs on these, biophysical or these physical feedbacks.
Yeah, that's actually a very good point. So right now we make the assumption that the reservoir that is constructed just takes over the temperature of the lake, which is currently in the grid cell. So we don't take that effect into account. But I think it would be very interesting to do that. But then we would need to make the distinction between reservoirs and lakes within the grid cell, so that's a good point.
Are we out of time?
No, we actually have a little bit more time.
Okay. Zuli Wo asks, why the albedo difference between the simulations with lake and just land in the fall and winter are negative?
It's just because the reservoirs have a darker surface, so a lower albedo. Yeah, I don't know if I can. So yeah, it's just the darker surface.
And then Yana Kalasa asks if you're looking at planning to investigate how the surface flux anomalies then propagate through the atmosphere to remote impacts.
Yeah, so currently we don't see any remote impacts like the internal variability. Like I only showed the statistically significant responses of the atmosphere, and there didn't appear to be any remote feedbacks. So everything was very localized. But I think one of the main issues here is the resolution. So to be able to look at this in more detail, it would be useful to also go to higher resolution models, maybe using this new WRF CESM coupling, which Dave was talking about yesterday.
yeah, I think that'd be really interesting.
Yeah.
Okay, we should move on. Thanks a lot, Ina.
Okay.
The next speaker is Farshid Fafalani. So go ahead and take it away, Farshid.
Yep. Okay. Hi, everyone. My name is Farshid Fafalani, and today I'm going to talk about the representation of interstellar groundwater flow and aquifer pumping in the community model. And this is work that we've been doing with my advisor, Dr. Yaru Pokrel, and Dr. Dave Lawrence for some time. And the first phase actually was recently published in Water Resources Research. So I begin with these challenges in larger scale groundwater modeling. And by larger scale, I mean the groundwater model in the two types of hydrological models, land surface models and global hydrological models. And we have some examples on the top from global hydrological models. And on the bottom, it's some land surface models. So groundwater dynamics in larger scale hydrological models is rather poorly parameterized or very simple, mainly because of limited data available for subsurface. Groundwater is often represented as a linear reservoir model in many of these models. And surface water groundwater systems are not fully coupled. And some of the main processes, such as human activities, for example, pumping, and lateral groundwater flow are missing in many of these models. So in order to address these challenges, this study is set to improve the representation of groundwater and irrigation interactions in the community land model by explicitly accounting for lateral groundwater flow and groundwater pumping in order to have a more realistic irrigation scheme while accounting for conjunctive water use for irrigation. And so for the lateral part, for the lateral groundwater flow, I use two approaches. The first one is based on Darcy, which was first used by FAN at 2007. It is the groundwater mass balance that we have the storage change equals to vertical fluxes like recharge, and then lateral fluxes like base flow and lateral flow. And then for steady state and for his slope cell, the recharge is kind of balanced with lateral flow, and this lateral flow is simply based on the Darcy's law and the head difference and transmissivity. So this is under a natural condition. I have the scheme here, so we don't have any pumping in this setting. But when we have pumping, like the figure here, so the larger head difference triggers a larger lateral flux. So I used the well equation, if you write it down in radial form, and if we can analytically solve it with applying pumping as a boundary condition, and then if we solve for this Q pump or Q lat or 1/8 of Q pump, then we can get the lateral flow based on the head difference again, and then we have some recharge terms, and etc. So these were the two approaches for lateral flow. And for groundwater pumping, again, it is based on the water balance of the grid cell. We have this pumping flux here, and this is calculated based on the irrigation demand, a ratio of irrigation demand that is satisfied with groundwater, and that ratio is simply based on the USGS census data that I show here. It is from 1985 to 2015, and for example, for high plains, we see that more than 90% of irrigation is satisfied from groundwater. And then when we remove the groundwater, when we remove the pumped water from either the groundwater aquifer or the soil water here, depending on the location of the water table, then we update the water table depths based on the specific yield. So the experiments are set in order to represent all four possible combinations by turning on and off pumping and lateral flow. So the first simulation is no lat, no pump. It is just a control simulation. And then the second simulation is no lat with pump, in which only pumping is activated. The third simulation is with lat, no pump, in which only the lateral flow is activated. And because we don't have pumping, it is based on the Darcy. And the fourth simulation is with lat and with pump. So both lateral flow and pumping are activated here. So the aquifer layer is also active for all 4 simulations, and the lower boundary condition is head-based. Spatial resolution is 5 kilometer, and then the simulations are conducted for 1998 to 2016 from forcing by anal gas. So if you look into the groundwater table depth, these are the 2 simulations without lateral flow. So this one doesn't have pumping either. So it mostly reflects the climate patterns, kind of shallow groundwater on the eastern part, and also the much deeper and much more variation on the western and southwestern. But when we add pumping, we also have large depletion in these regions of highly irrigated, like High Plains Aquifer or Central Valley. And when we add lateral flow, then these 2 are the difference of water table depths between the simulations with lateral flow and without lateral flow. And you see that the difference on the east is mainly negligible, mainly because of the very small head gradient on the east part. But on the west, that we have a large variation of head, then the head gradient actually triggers large lateral flow in both cases, without pumping and then with pumping as well. So if you look into these 2 specific regions that we have data to validate, in the High Plains Aquifer. So we have USGS reports for 1950 to 2015 that shows that the cumulative water level change for High Plains shows up to 50 meter of depletion in the central part in Kansas, and also large depletion in Texas, in the southern part of High Plains. And if we compare it with the simulations here, the top 2 simulations do not include pumping, so we don't see much of these hotspots here. It's based on just the climate and the recharge. But the bottom 2 simulations actually have pumping activated, and we see most of these hotspots nicely pop up in these blue regions. And if you want to see, if you want to focus on the impact of lateral flow, just comparing these 2 insets here. So the case that we don't have lateral flow, the water table is kind of artificially pixelated. But when we have lateral flow activated, then the convergence of groundwater from surrounding areas can actually form a more realistic, larger scale cone of depression. So if you compare it with previous studies, like the one by NEED 2018, it's from NORMP, and the period is kind of similar. It's 2002 to 2015, and also another study, DGRAPH 2019. The simulation period is longer. It's 1960 to 2007. We see that the CESM simulation here seems to relatively better capture these special patterns of groundwater depletion. And if you look into the time series, again, these are the 6 regions for these 6 blue boxes here on the right. And we have 4 lines. The green and blue lines are for the simulations without pumping. And the red and purple are for the simulation with pumping. So we see that when we add pumping, this depletion can be nicely, again, followed by the simulation. And these scatters are actually the pump, the well data. And but because we are averaging over a region here, like so the difference between these 2 lines, I mean the impact of lateral flow is kind of insignificant, mainly because of averaging over a region. So those plus and minus fluxes actually cancel out. And this is true for many of these regions across High Plains. Now, if we looking to Central Valley Aquifer, for Central Valley, we don't have that kind of regular reports like in HVA. But this is the estimate that we have, one of the best estimates that shows the groundwater depletion for 1860 to 1961, and shows a large up to 120 meter of depletion in the southern part, in the San Joaquin Valley, and also in Tulare Basin in this area. And if you compare it with the simulation, again, in the simulations without pumping, we don't see much of this depletion. But when we add pumping, again, the depletion, actually, the hot spots of greatest depletion pop up in the southern part. It's a little bit shifted compared to these estimates. It's towards center. but our simulation period is outside this period. So we cannot do a very one-on-one comparison, but it shows us also that the simulations also have some showing the depletion up to 15 meter in the southern part. And again, if you want to see the impact of lateral flow, we can compare these two. Again, here we have smoothen water level change when we add lateral flow. So we can also show this lateral fluxes as a flow field. I adapted this from the concept of wind velocity fields. So to show the lateral flow, it's a little bit noisy, but if we focus or if we zoom into some areas here, for example, in the central part of High Plains Aquifer, you see that the water is converging from surrounding area, and that the magnitude of these arrows are up to 3.5 millimeter per month. And this is also nice. This is kind of a nice representation that shows how water actually moves toward the largest depleted region. And the same case here in Central Valley, again, in southern part and central part, we can see these flow fields. So let's lastly look into the terrestrial water storage trend. These are the trend maps for 2005 to 2015, and these are from GRACE solutions. So we already see some uncertainties among GRACE solutions, like here in Great Lakes region. If we compare it with the simulations, already show the two simulations actually. This is no pumping and this is with pumping. The other two simulations are similar because I used that filtering stuff to be able to compare it with GRACE, so that the impact of lateral flow is very negligible here when we do those kind of things. So when we add pumping here, we see that the negative TWS trend over Central Valley is nicely captured compared to the situation that we don't have pumping. But we also have some overestimation across High Plains, especially in the central and northern part, which remains actually an issue still, because it was also reported in previous studies as well across High Plains. So to wrap up, the new groundwater model equipped with pumping, lateral groundwater flow, and conjunctive views. When we activate the groundwater pumping, it improves the simulation of groundwater level change, both spatially and temporally. It could capture most of the hotspots of groundwater depletion and also capture the GRACE detected downward trend in areas such as Central Valley. But the caveat is that it overestimates a decline in TWS across some part of the High Plains. And when we add lateral flow, we could improve to some extent the subsurface response, especially to pumping. And it tends to smooth the pixelated actually groundwater level change to form a kind of more smooth cone of depression. And but the impact is not substantial at basin scale or coarse grades. So the path forward from here is so we have discussion with Dave to include some, to leverage actually newly available data sets like the global aquifer properties. I have 3 examples here, like the permeability data sets from Gleason, or depths to bedrock, and also the aquifer thickness. These are the mostly new papers. And we can also do some calibration. I didn't show anything about the river discharge, but the river discharge didn't show much sensitive to water level change even after adding pumping. So probably we need to do a kind of calibration of some of the subsurface parameters like the runoff parameter. So with this, I would like to thank you and for taking a question. Thank you.
Great. Thank you, Farshid. I think we have a time for maybe a question or two.
Yeah, there's one question in the chat from Mauro Sulis asking if you looked at the impact of the lateral flow and pumping on the surface energy fluxes.
Yeah, that's a great question. No, actually, this the focus was mostly on the hydrology part and in terms of the water actually fluxes below the subsurface. Yeah, but that's a good suggestion. Thank you.
Peter has a question, but I also like to ask a question. It might be the last one. Maybe you can answer Peter's. Is you didn't really comment on the new feature, one of the new features, which is the grid cell to grid cell communication in the model that you had to implement to be able to allow this, which is an infrastructure. Can you make any simple comment about that? And if not, we can.
Yeah, sure. So we've been talking about this, pushing this to the CTSM code base. And this is a little bit different to what there already is. There, like the within cell, intracell, within cell lateral flow that is kind of field slope. But this is kind of between grid cell to grid cell, and this could be actually more beneficial for studies like smaller domains or higher resolutions, that we can have this between cells lateral flow.
Okay, great. Thank you, Farshid. There's at least one more question. Others might come in, so please address those. And we'll move on to our last presentation in this first session. So it's from Yeliz, talking about snow cover. So go ahead, Yeliz.
Hi, everyone. Let me share. My name is Yeliz Yilmaz from the University of Oslo, and today I'm going to talk about benchmarking CLM5 snow cover dynamics with MODIS and reanalysis over Fennoscandia. It's a regional study done under two different projects that also are some of NCAR colleagues are involved in. One is Lattice. Lattice is focusing on land-atmosphere interactions in cold environments, but by combining these different approaches, it's not only modeling, but it includes laboratory measurements and extensive field studies. And the other one is Emerald, a sister project. It is focusing on terrestrial ecosystem climate interactions by using, again, CLM. And my study actually started with this analysis from CLM simulations over this region. We conducted satellite phenology simulations out of the box, like 14 years simulation period at a quarter-degree resolution, forced with GSWP3, and we were comparing these results with GRACE data. And what we saw was like some agreement over the mainland, and in this Svalbard part, which is a glacier area, there was like a big magnitude difference. But then we focused more on this terrestrial water storage anomalies and how they are related with the snowpack changes. And of course, everyone knows CLM, but why we are interested in with CLM is because it's the land component also of Norwegian Earth System model. And in this study, we are also using several climate reanalysis products and also satellite remote sensing, particularly from MODIS. And our first question was, how does CLM5 perform compared to the observational data set for snow? And we first used 4 different reanalysis products at different resolution. And when we map this snow water equivalent values over the whole region, we saw, especially over Norway, this mountainous area and Svalbard, the biggest disagreement was over Norway. And when we compared CLM5 for each season with this 4 different reanalyses, what we saw for winter and spring was over this coastal area is the mountainous area, CLM is overestimating SWE values, except this southern Norwegian part and Svalbard. So when you also average over this mainland part, what we saw in this blue line was CLM was always overestimating at monthly scale over the time. There is a big disagreement in Svalbard, which is a glacier region. So because of that, reanalysis products show different behavior, but it is another topic. And this is why we decided that we need a representative baseline snow cover map. So we turn our face to remote sensing because we are living in satellite era, and Terra and Aqua has almost 20 years of measurements at different resolutions. So in this study, we are using high resolution daily and 500-meter special resolution products, and we are combining both. Just to give an overview, MODIS data are stored in tiles. So we are using these 4 tiles over Scandinavia, and it is a long processing step. So first you need to stitch these tiles and create your map like this. And here we have the polar night conditions, and yellow ones are the cloud cover. So by combining both satellite, Terra and Aqua, we can reduce the cloud cover. And we have this daily normalized different snow index values for each year. But we are calculating mainly snow metrics and fractional snow covered area from MODIS. This is our workflow. From NDSI, we are calculating fractional snow cover area, and then we gap fill the cloud areas. And then for each water year, we are calculating snow metrics. These are snow cover duration, first and last day of snow, and some uncertainty metrics for cloud persistence. So eventually we have the 6 metrics for each water year without any cloud. We are happy for that. At least it was a long processing step, but done. And then we want to look at how does CLM5 simulate snow cover phenology. And we did the same with CLM outputs. It was okay. And when we put them next to each other, on the top panel, you see MODIS. On the bottom panel, you see CLM5 for snow cover duration and first and last snow days. If you use your imagination, they have some kind of, it can be comparable, at least this is what we can say. Of course, the MODIS data at 500 meter resolution, and CLM is at 25 kilometers. So we needed to regrid MODIS data. So here you see some practice with this regridding. In the first one, you see the native MODIS grid cell. In the second one, it's ERA 5 land, and the third one is CLM5. But we aggregate basically MODIS pixels over this CLM grid cells to be able to compare how it does. So as an example, for this particular water year, what we see in this x-axis is MODIS. On the y-axis, we see CLM5 and ERA5 land. It has some agreement for snow cover duration. It is comparable, at least. So this is an ongoing study. These are the preliminary results that I wanted to show. But here is our main idea is to force CLM5 with ERA5 reanalysis data to be able to reduce this, at least address the uncertainty from the forcing data set and this difference in the snow models. This is ongoing, but we did some tests with ERA5 forcing at a point scale at Finse site. Here you see the temperature, it has some match, and for wind, it was underestimating. And ERA5 was underestimating compared to observations. And we will look at the snow depth. These are like time series from 4 different grid cells around this point scale point. And since it is a glacier region, as you see, some points doesn't even have snow-free season. So we needed to bias correct this data. And when you apply the same bias correction to compare wind values, if we focus, especially you see here, the black lines are our observations at the covariance tower, and the blue ones are the bias corrected ones, and they are matching not bad. So it is ongoing. We will use this forcing at the point scale. And of course, main question is how accurate are the MODIS retrievals? So we needed to do a validation at local scale over Finse and regionally over Scandinavia. We are focusing this Finse, it is in southern Norway, because we have an eco-hydrological observatory that from Lattice project. It is a low alpine site. We have a lot of snow surveys and camera images and etc. So here we are using around this site, Sentinel-2 and Landsat-8 high-resolution satellite images. On the left part, you see the false color image directly from the satellite, and we can retrieve this fractional snow-covered area values from both satellites. So this is like a spectral unmixing algorithm, and this is ongoing, and we are really processing a lot of satellite images. And as I said, we have some aircraft and terrestrial photos at this region. For example, for this camera images, it's installed on top of a roof and it's looking at this hill, and we can map these images on DEM, and we can have the snow-covered data. So this is another independent source of data source to do some validation. Another data set that we are using over whole Fennoscandia is actually this Sentinel-2 operational snow product. It's just became operational, and it has 20-meter resolution since 2016, and it has another cloud mask using another algorithm to extract this fractional snow cover area. So we are using these tiles based on their representativity for this tree covers density. It's ongoing. It's a collaboration with a colleague from CESM in France. So we have a long validation chain. Basically, we are using aircraft and terrestrial photos to validate this high resolution satellite retrievals at the local and the regional scale. By using them, we will validate MODIS, because MODIS has long-term snow record globally. It's an important one to be able to understand CLMs, for example, snow processes, because these satellite data sets give us at the same spatial representativity, the information at the same spatial resolution, at least, for Earth system models. And our actually next step is to first understand and improve the snow processes by using the satellite images. And if we can conclude that, we are going to extend this analysis to Pan-Arctic scale. And we are currently also working on improving fractional snow-covered area parameterization as an initial snow process implementation. So thanks for listening. This is all for now.
Great, thank you, Yeliz. We have time for some questions. So again, please raise your hand. Have a question or put it into the chat.
Sinlin, who asks in chat if you've looked at the snow water equivalent?
Yeah, snow water equivalent, to be able to have that data, we need some data assimilation, because you cannot get this information directly from satellites. We have a study for that too. It's a side study, but it includes data assimilation. Not yet, so the answer.
So Yeliz, Steve, I have a question or a comment. So one, with your analysis so far, can you summarize your understanding of strengths and weaknesses of CLM, or do you feel like you're not quite ready to make any statement like that?
Yeah, we are not.
You showed results very quickly, like you showed comparisons, and I couldn't study them.
Yeah, the whole analysis actually is going to, it's not, as you saw, we don't have the final products yet, but we want to focus on, for each PFD type and a different elevation level, the performance of CLM to be able to address that, because there's a big mismatch, but we don't know the source yet, but it is on this complex terrain, right, on the mountainous region. So we know the region at least, but we are not so sure about the processes yet. So it's a bit early to say something, but at least on the large scale, at the regional scale, we are trying to produce this representative data set to be able to talk more accurate.
So another comment, while we're waiting for, it looks like Andy has a question. So let's let Andy, do you want to ask it, Andy?
Yes, I was just wondering whether the snow depth, snow covered fraction relationship, which I think CLM uses, does that vary with grid cell resolution, or should it vary with grid cell resolution?
Yeah, this is another question that we are curious about. Actually, there is another project that we are involved that produces snow depth data from ISAT-2 satellites at our section. So we are hoping to use that also product to understand this relationship, but everything is like not so mature right now to talk yet.
Yeah, Andy, there is no grid cell resolution size dependence for the snow cover fraction parameterization, except to the extent that I think an input parameter is the subgrid topography variability. And so as that changes, as you change resolutions, that could affect the overall. And I'll just note that we do turn it off, I think, completely for single point simulations. So there is no snow cover fraction parameterization in typical single point simulations if it's done correctly. I think that's correct. Because we're assuming that at that scale, it's not really quite capturing the right thing. The comment I was going to make real quick, and then I think there's another question, and we are kind of moving into discussion phase. So I think if anyone has any comments or questions, we have about 10 minutes on any of the presentations, please chime in. But I think and this is really relevant to several of the presentations we saw today, is this, Sean's hill slope capability. We don't have any talks this time from the hill slope model, but Sean has been making progress, and I'll just quickly summarize that one of the big new features, in addition to slope and aspect, is a downscaling. And so he is downscaling precipitation. He's tried several different methods and trying to finalize it. And hopefully we'll be able to present on that at least at a CLM meeting soon. But it's showing quite a bit of promise about capturing this gradient in snow across, the elevation gradient, even without capturing the full resolution. So even if you're going to 25 kilometers, you're not really capturing the gradient, right? So I think the hill slope model is useful down to maybe even 5 kilometer resolution or lower to capture some of these things that are happening sub-grid scale. So hopefully we'll have more news on that soon, but that is, I think that could really have a strong impact. And I think, Elise, your case study might be a great application of this, because you're really looking at a complex terrain situation in Norway, and you just can't get it at 25 kilometers. It's just not possible.
Yeah, exactly.
So there's a couple more questions for Elise, and also I'm wondering if anyone wants to raise any of the, I know there's been a lot of chat stuff that's been going on, which is kind of fun to try to monitor the chat and watch talks as well at the same time. So everyone's hopefully able to multitask there. But Andy is suggesting this grid scale aware snow cover fraction formulation would be a good idea, especially for WRF CTSM. And I guess I agree. I wonder, Andy, if Sinlin is saying, Sinlin, do you want to expand on your comment?
Yeah, so we have a pending proposal to trying to improve the snow cover formulation across scales using the multi-satellite data and also the machine learning methods to do that. Hope that we could get funded, and then we could look at this scale-aware snow cover formulation issues.
Yeah, this sounds really exciting. Actually, we have side projects, as I said, but none of them came to fruition yet, especially for testing with some ensemble simulations. But next year, maybe we can talk more.
I'd like to come back to Hadrian's presentation and a comment time with the chat and let Hadrian expand on a little bit. Is that, I was a little bit concerned about those really large biases in the summer. 5C is pretty in a pretty large bias, right? So I don't know if you want to expand any more, Hadrian, on your understanding of the source of that bias, whether it's a feature of CLM or the forcing or some combination, and whether it's a summertime problem or something that originated in the winter that's kind of extending into the summer. If Hadrian is still here, maybe she's stepped out.
No, I'm here. So
okay.
So you're talking about the maximum annual ground temperature plot. Mm-hmm. And so maximum annual ground temperature is typically like originating in September, and then once you move downwards, also the timing kind of moves, right? So it's like a late summertime, early autumn time problem, probably. So I know that the atmosphere does have a cold bias, a rather pronounced cold bias, especially over eastern Siberia in wintertime, which stems from circulation problems that the model has. And this could, of course, also in the long term translate into the maximum annual ground temperatures. Yes, but yeah, so we need to look at the details actually. And then, like you said in the chat, switching to CLM5 might actually make the problem even bigger. So we need to look at that. I actually can't really, I have done offline simulations and with meteorology forcing, but I haven't looked at them yet. So maybe that's going to give us an idea. I also have done some offline simulations where the feedback between CLM and the atmosphere is switched off. So I can see, or I can kind of get an idea what is feedbacks and what is driving. But I have to look at those. I haven't looked at them yet.
Would anyone else like to make any questions or comments about this set of morning presentations?
I can jump in.
Yep.
Sorry, I was trying to model good behavior. Yeah, I guess I hadn't heard anything about the groundwater work, so that's exciting to hear. And I'm also, yeah, instantly my head went to like, oh my God, how are we going to include this along with all the other hydrology work that's going on? And I don't know enough about it to be able to guess what the conflicts or challenges are. Yeah, I guess I'm curious how to integrate that with hill slopes and with the new river model and everything else that's going on.
Well, there's the question of integration of everything, and there's also just the question of getting the capability and then worrying about how it integrates.
Yeah.
And so the way I'm viewing it is to the extent that Farshid is able, and he's got his own other things that he's working on. But if we could bring in this capability, especially the grid cell communication, and we already have a groundwater pumping scheme, so
right.
We need to sort of compare and contrast where things are different. But it's the the key elements are the lateral flow and grid cell communication, especially at high resolution, and then the the equations that are determining that groundwater flow. We can compare and contrast those to the existing hill slope model, and also Yingfan's model and things like that. But and then the data sets that need to go with it. And so those two things, once we kind of get those in, then we can start asking questions. Is it even possible to think about how to integrate hill slope and grid cell to grid cell? And maybe it's just too complicated, right? But we could also then evaluate the value added from the different solutions, and it's probably problem specific.
Yeah.
But again, sorry, I'm monopolizing here, but in terms of like moving towards this, towards the WRF or the weather applications, I think having this feature is pretty important because NP already has something like this. And so one reason that they're going to be reticent to adopt CTSM is that we do not do lateral groundwater flow. Now, Sean might argue that it's not really that important, and he might be right, but we need to be able to do it to demonstrate that, or demonstrate that the hill slope model is just as or more effective, but until we can prove any of these things, getting them to adopt CTSM as the WRF community at high resolution to adopt CTSM is going to be challenging. It's a lot of moving parts, so that's pretty
per usual. It looks like it's 10:30, and so we have a break now, and I scheduled this as a virtual coffee break. So there's no snacks, and if the coffee's bad, it's your own fault. But I think what Elizabeth will do, we'll set up breakout rooms that we can choose to go to. So if you've got, and this will only work if you have an updated version of Zoom. So if you're interested with talking with people, I'd encourage you to stay online, or take a break, go for a walk, and then come back, for the last 10 or 15 minutes of the coffee break, and meet some people. So you can go into a breakout room, have a conversation. I think you'll be able to see who's in other breakout rooms. So if there's somebody that you've been wanting to talk to, or you want to follow up with one of the presenters that we've seen over the last couple of days, it's a good time to grab somebody, hopefully informally and a little bit more like an in-person meeting.
Do you know, Will, if we can like leave one and move to another one?
I think in other meetings I've been able to do that. Maybe, I don't know if Elizabeth has any advice for us on how this can work.
Yes, I've set it up so that you can choose your room. I've set up 11 different rooms, so it allows for some small group discussion. It should work where you can see who's there, or you can pop in and out. No one will have their feelings hurt. And if you can't move and you come back to the main room and just say hi to me or put a message in the chat, and I'll move you to another room. It's an experiment. We're going to give this a try.
Yeah, so if it goes well and people like the freedom of being able to move around and choose who you talk to, then we'll do it again tomorrow. And if it's frustrating and doesn't work or whatever else, then tomorrow Elizabeth will just put us into breakout rooms randomly, and you'll get to enjoy talking to whoever you're placed with, which we've done at several meetings, and it's kind of fun just to meet somebody new and have new friends. And Elizabeth, will you bring us all back at just before 11?
I will force you back. You'll just have I'll send some warnings, but otherwise there's a 10-second countdown, which does appear very small. Some people say that they miss it when I do send messages to all the rooms, but all of a sudden you'll just disappear and come back to the main room.
Sounds good.
So the rooms are open. Like I said, there's 11 of them, and you can go ahead and choose. So it should be at the bottom where it'll say join a breakout room.
Cool. Great. Yeah, so don't worry about joining a breakout room if you're going to go use the bathroom or something, but then when you are back and you want to chat.
I'm going to make a cup of coffee and I'll be back in 5 minutes.
Yep.
Probably love to do like that.
Yep. Yeah, likewise. All right. We'll see everyone in a little bit.
Hey, Elizabeth, I can't figure out how to move myself. Can you put me in room 1? Seems like that's like a default place.
Sure, Charlie, no problem. Now you should see an invite to join the room.
maybe before we get started, do people enjoy getting to choose their breakout rooms? Thumbs up, thumbs down. If your video's on, I can only see like 4 of you, so. Yeah. So if you strongly didn't like, I enjoyed it. If you'd rather be assigned to a room, go ahead and put that in the chat, and we can have an informal poll. Maybe I'll even make a poll for this afternoon.
I did switch rooms once, so I mingled.
Oh, that's good.
I successfully mingled across groups. So,
gold star.
I figure it's worth a shot. It's all experiments.
Great. Should we go ahead and get started with the rest of the morning talks?
Yep. So I think the first presentation in this next session is by Mauro Soulis. So, Mauro, why don't you take it away?
Okay. Do you guys see the screen now?
Yes. Perfect.
Perfect. Okay. Hello, everybody. My name is Mauro Soulis. I work at the Luxembourg Institute of Science and Technology. Today, I'm going to present an evaluation of CLM5 across an environmental gradient in Europe. And this presentation is part of a project funded by the Luxembourg Research Fund. And I would like to thank the valuable contribution of all the co-authors listed here. So in a nutshell, the overarching objective of this project is to investigate the influence of plant hydraulic trait variability and covariability on the simulated evapotranspiration response across different ecosystem and environmental gradients in Europe. The project is based on 3 main pillars: numerical simulation, information extracted from plant functional traits database, and thermal remote sensing. The numerical simulation are conducted using CLM5. Today, I'm going to present the results of point-scale simulation across 6 sites in Europe. The sites are listed here, and these are forested sites. For each of them, we have a different time period, different plant functional type, and different plant species, tree species within the eddy covariance footprint. And we have a nice gradient in terms of mean annual precipitation, temperature, and VPD. So from a methodological perspective, we have the setup of the model consists so in point scale simulation that we defined using the CLM5 tools. Then we created a workflow to connect, let's say, the atmospheric forcing from FluxNet data to CLM forcing. And for that, we use a FluxNet LSM tool developed by Ukola et al. And then we updated the LAI values, so using the glass product at 0.01 degree. And so it means that instead of using a prescribed phrenology, the constant year by year, every year we re-update the LAI phenological development. We compare the results of the model with respect to latent heat, sensible heat, and GPP from FluxNet. And then this information is complemented with transpiration fluxes as extracted from subFluxNet database. So what I'm showing here is is the overview of the model response in this, let's say, default configuration across these different 6 sites. And what I'm reporting here is the 15 days moving average of daily cumulative ET. What you can see from this slide, it's clearly, okay, the blue line, it's the measurements, and the red line it's the model. I'm going to use this convention throughout the presentation. What you can see clearly here is that there are sites, let's say in Finland, Itialla, where the model nicely pick the interannual variability of ET. And there are other sites, let's say this on the upper left here in France, in Pucabon, or the lower right in El Saler in Spain, where the model show some certain problems. I'm going to focus now in the analysis today on the Pucabon, where we have a long-term series, and then, but we are looking also more carefully also on the other side. What we do as a first is we look at in this plot on the relationship, for instance, between GPP and relative humidity and GPP and 2-meter temperature from the observation and from the model from two contrasting sites. So Pucabon in France, relatively hot and dry site, and Itialla, which is in Finland in the northern part. And what you can see is in the northern side, the model is nicely reproducing this GPP versus relative humidity and temperature pattern, where in Pucabon, what we see is there are identified some spot where the model systematically underpredict GPP. Okay, with this we look at on the annual scale. Okay, on the annual cycle of ET and GPP, and here I'm reporting the results for one specific year, but which is pretty much representative of the model behavior at this site. What you can see is that in the default configuration, the model tends to overestimate the total latent heat, especially in the first part of the season, and we identify a sharp decline of GPP during summertime. So this gave us some sort of indication that there is some sort of imbalance, maybe too much soil moisture during the first part of the year and too less moisture during summertime. And for that, then we look at what you can also see here from this slide is that when the model also largely overpredict latent heat, it doesn't overpredict GPP. So this also gave us another sort of indication that something is mostly related to the ET partitioning. And then we made a check, and then we test on the different soil resistance. So we change the dry surface layer. So actually we increase the soil resistance to let the water more into the system during the first part of the year and to have more moisture during the summertime. And then you can clearly see now what's happening is that now the GPP is really nicely reproduced also during summertime, but we still have overprediction of the total latent heat, of the total ET during the first part of the year. I'm going to be back to this later on when we look at the transpiration fluxes. So once we have done this, we are interested, as I said from the beginning, on the plant hydraulic parameterization. Okay, what I'm plotting here, what I'm reporting is on the left plot the distribution, for instance, of the P50 value across this for the different site as extracted from different database. Okay, in the inside the box we have the default value assigned by the model, and what it's here, it's nice to see is that for some specific sites, we have an intraspecific variability. And for some other sites, we have interspecific variability. For Pucabon, this site that we are looking now, we are looking at, we have just intraspecific variability, okay? And on the right plot, what I'm showing is the simulated plant vulnerability curve using these different P50, okay? And as you can see, moving from the red to the blue, actually you are allowing the plant to operate a different leaf water potential, okay? And with this different configuration of P50 now, we look at the response in terms of transpiration, okay? So now we are looking not on the total ET, but we are looking on the transpiration component, and we are comparing with the information as extracted from the subflow data. And what I'm reporting is that the variability in P50 for the model, and for the observation, we are reporting the variability across the sensors. And what you see here is that the model still overpredict also the transpiration component, okay? This is especially true for 2010, where we have higher precipitation, a large amount of precipitation during the first part of the year. The way we interpret it is, for this site, we have a shallow bedrock, okay? So we have that, the model tends to be really relatively wet during the rainy season, okay? And this shallow bedrock then tends to create, explain, let's say, this higher transpiration, systematic higher transpiration also during the summer period. Now, what I'm showing here is the relationship for this set of model sensitivity analysis between the stomatal conductance and the total transpiration from different P50 values. And what you can see here nicely is that when you move toward more negative P50, you're let the plant to transpire more. So you have an increase of the total transpiration. And what you have is that also for more negative, so leaf water potential, you have still the plant transpiring. So in this plot is what I'm showing in this, it's the clustering over different leaf water potential. For the right interpretation of this plot is you do not have to consider all the red points as a water stress, okay? It's just to show that changing the P50, the model operates a different leaf water potential. And on the bottom, I'm showing the effect of the shape parameters of the plant vulnerability curve, okay? And using, let's say, a more steep curve with a CK equal to 6, and a more smooth one on the right with CK equal to 2. The effect of CK here, it's clear that the total T doesn't change much, and what it's just basically changing is the range of operation into the model. And this is more clear from this picture. What I'm showing, the relationship between the beta factor, so the limiting factor, and the leaf water potential for this different P50 value and the different CK, okay? So with this, I'm gonna move to the conclusion of the presentation. So in general, from this experience with this simulation, we can say that CLM5 nicely capture the ET variability across these 6 forested sites. The soil resistance largely explain some model deficiency in ET partitioning at some site. This is especially true for Pucabon and El Saler. I'm here in this presentation, I show the results of Pucabon, but the effect of soil resistance is quite clear also for El Saler, where the default model configuration largely underestimate the total ET. And then what we can see from these results is that the intraspecific variability of plant hydraulic parameters strongly affect the simulated transpiration response during summertime, but the uncertainty bounds do not always extend to the observed ET. So basically, variability in the plant hydraulics do not explain some model deficiency. With that, I would like to conclude my presentation and will be happy to take any question.
Thank you, Mauro. I think we have time for a few questions if there are any. As before, raise your hand or put something into the chat. Oops, my hand is raised, but I didn't mean to do that.
Dave, do you have a question?
I do have a quick comment while people are thinking is Mauro, that's interesting. I was curious. Well, one is a question. Did you, when you changed the dry surface layer parameterization, did you try it for all sites, and did you see like a degradation at the other sites, whereas an improvement?
Yeah, this is an extremely good one. We tried through the sites, all the 6 sites, and the change do not go to the same direction everywhere. And if I have a few seconds, I want to show this one for these sites in El Saler. I don't know if you guys see the slide now.
No.
So
hidden slide. We're not seeing it.
Okay, let me. Okay. The effect of soil resistance is that, for instance, in El Saler, we had actually to get a better match with the observation, we have to decrease the soil resistance. Okay, so as an effective, so the model is really sensitive, but instead of increasing the soil resistance, we have to decrease for El Saler to have a better match. That's the point.
So we should probably move on, but I'll just make one comment for everyone, is that in CTSM 5.1, which we talked about yesterday, Daniel Kennedy has reparameterized the values for many of the plant hydraulics parameters, and the main idea there is just to bring them closer to the stress level for essentially all the different PFTs as our default starting point for the parameter perturbation experiment. So just so anyone's aware of that. It looks like there's a question, but I think we should move on and we can maybe return to this during discussion. So the next presentation is by Claire Zaracas. So Claire, Mara, if you stop sharing.
Wait.
Usually it's in the upper.
Yes, sorry.
Yep.
Sorry.
Okay, no problem. So Claire, why don't you go ahead?
All right, so are you seeing my slides and hearing me okay?
Yep.
Yeah, your volume's a little bit low.
I'll put on headphones really quickly and then get started. Okay, is that better?
No, that's worse. Maybe take off that. Yeah.
Yeah, I think it was okay.
Yeah, it was okay. Just
but do let me know if you have any issues hearing me or if it gets. Okay. So I've been working on parsing apart the relative impacts of temperature and VPD on tropical forest GPP. So the big picture motivation for this work is that we don't know how tropical forests will respond to warmer climates. So some observations indicate that tropical forests may have a high temperature limit and that they might already be near that limit in the present day. But this is debated, and photosynthesis can decline at high temperatures due to these 2 different mechanisms. So firstly, there are biochemical responses to high temperatures that can drive photosynthetic declines. And then secondly, stomatal responses due to increasing vapor pressure deficits associated with high temperatures can be a more indirect driver of GPP declines at high temperatures. But the challenge is that in natural tropical ecosystems, temperature and VPD are really tightly correlated, so it's hard to parse apart the influence of temperature versus VPD on observed changes in photosynthetic rates. But in a recent paper led by Marielle Smith, she and co-authors took advantage of an unnatural ecosystem. So an experimental tropical forest in Biosphere 2, which is pictured here, to disentangle the different effects of VPD versus temperature in observations. So the key feature of Biosphere 2, which makes it useful for this question, is that it's much more humid than natural tropical forests, even at high temperatures. This figure is from that Smith et al. 2020 paper, which shows the relationship between temperature on the x-axis and VPD on the y-axis for a few sites in the Brazilian Amazon, shown in blue, a seasonally dry tropical forest in Mexico in yellow, and Biosphere 2 in red. So Biosphere 2 can get really hot, a lot hotter than the Amazon sites, but even at these really high temperatures, like 35 to 40 degrees Celsius, it still maintains a pretty low VPD because it's an artificial environment, so it can stay really humid. So in this paper, Smith et al. Look at the relationship between light saturated ecosystem level photosynthesis and temperature at these different sites. This figure is from that same paper, showing the light saturated gross ecosystem productivity on the y-axis scaled to the maximum value, so that's 1. And this is showing hourly GPP binned by temperature. So this line shows the relationship for these sites in the Brazilian Amazon, and there's a strong decrease in light saturated photosynthesis with increasing temperature. And there's a really similar temperature response curve for this other site, Tesopaco in Mexico, which reaches much higher temperatures and higher VPD values than the Amazon sites. But then at Biosphere 2, which is shown here in red, there's this much more gradual decline in photosynthetic rates of temperature. So even at 35 degrees Celsius, gross photosynthesis has only decreased by about 20% from peak levels. So it's able to maintain high photosynthetic rates even when it gets really hot. Meanwhile, all 3 of these sites have really similar responses to VPD. So this suggests that this apparent steep decline in photosynthesis at high temperatures in these natural ecosystems might be driven more by stomatal responses to VPD rather than that direct biochemical response to high temperature. So this has implications for tropical forest resiliency. If the GPP declines at high temperature were driven directly by temperature, so if the biochemical responses were stronger, that would not bode so well for forests under a warmer climate. But if photosynthetic declines were due to stomatal responses to VPD, as this paper suggests, we might expect some compensating effects from increasing CO2 concentration. So this would suggest that tropical forests could be potentially more resilient. And I think a modeling approach can complement this observational study really well, both because this Biosphere 2 dataset presents a pretty unique opportunity to test models' representations of these 2 mechanisms, these 2 different responses, and also because we can use models to quantify what about Biosphere 2 enables it to maintain these high photosynthetic rates, and to quantify the implications of these different responses to VPD versus temperature for tropical forest resilience. So we kind of get a qualitative sense from the observational study, but models can help us make a more quantitative statement. So I'm in the pretty early stages of this project. So my first step has been testing whether FATES is capturing the tropical forest GPP responses to VPD versus temperature identified by this paper at these different sites, which I'll talk through shortly. Then I'm also swapping elements between Biosphere 2 and these natural forest sites to isolate what's so special about Biosphere 2 that allows it to do well at these high temperatures. So I mentioned that humidity is a key difference, but there are a few other differences between, say, Amazon forest sites and Biosphere 2 that could interact with that, like CO2 concentration, different levels of sunlight. There's seasonality Biosphere 2 because it's in Arizona, as well as the dominant plant species that are there in different functional traits. And again, the goal of all of this is to improve our representation of plants' responses to VPD versus temperature. So far I've been looking specifically at Biosphere 2 and just one of those Brazilian Amazon sites. So I remade the same Smith et al. Plots I showed earlier. This figure is just my version, but it's still just showing observations for now. And I'll be showing a few more of this same kind of plot in temperature versus GPD and VPD versus GPP space. So let's see how FATES does here. This thinner blue line I just added shows the GPP response curves from running default FATES at this Amazon site, kilometer 67. So this is configured with one tropical broadleaf PFT calibrated to PCI, and FATES matches these observed GPP response curves, which is the thicker line, pretty well. But if we look at Biosphere 2, which is this thin red line I just added, FATES isn't matching these response curves as well at all. So in particular, we see that in FATES, Biosphere 2 GPP declines too much at high temperatures compared to the observations. And some of that strong temperature response is aliased into this VPD curve. So I'm adopting this approach of binning by VPD and temperature so that I can compare directly to these observations. But I've also run FATES with kind of synthetic meteorologies to distinguish between the VPD and temperature effects. And that makes it clear that it's really the high temperatures that are pulling this curve down. So this gap here suggests that FATES is missing some process. And one thing that we know we're missing in FATES is photosynthetic temperature acclimation, though that is implemented in CLM.
Say live, say live.
Oops. I think someone is not muted. Okay, we're good. So observations indicate that plants can acclimate and or adapt to the temperature where they're growing. So there's a temperature dependence of the parameters that determine photosynthetic capacity, VC max and J max. And that temperature dependence, or like the shape of these curves, changes with growth temperature. So this figure on the right is showing the temperature dependence of the potential electron transport rate, Jmax, at different growth temperatures based on the C3 temperature acclimation algorithm in this paper, Kumaratunge et al. 2019. So the solid green line is the temperature dependence at a growth temperature of 20 degrees Celsius, and the peak shifts towards higher temperatures as growth rate or the growing temperature increases to 25 degrees in the dashed line and 30 degrees Celsius in the dotted line. So without temperature acclimation in FATES, this curve exists, but it's the same everywhere and it doesn't shift based on the growing temperature. So adding this particular temperature acclimation scheme really flattens the GPP response to temperature. So it brings these lines up to the dashed lines shown here, which kind of aligns with what you'd expect if you think of plants acclimating to where the temperatures at which they grow. So we don't see that sharp decrease in temperature that characterize those default FATES simulations. For Biosphere 2, that means it's bringing the GPP response more in line with the observed response. But adding temperature acclimation also flattens the curve for the Amazon site, which doesn't align with observations at all. I don't have a complete explanation for this yet, so I'd be curious if anyone has any ideas, but I have a few ideas for areas to explore next. Broadly relating to functional traits, firstly, I'm using a parameter set that's calibrated to PCI, and it was calibrated based on these different scaling functions that didn't take into account temperature acclimation. So that old functional form might be kind of embedded in the parameter file in a way that's a little unrealistic. Additionally, there might be differences in key traits between these sites and BCI, or between Biosphere 2 and the Brazilian Amazon. In some like preliminary sensitivity tests, the stomodal slope parameter can really change how GPP responds to VPD and temperature, as can the stomodal model. So I'm continuing to work on configuring these runs to more accurately represent these two different sites in the plants that actually live there. I also wanted to make one quick note about the details of the temperature acclimation scheme I'm exploring here. So I know I'm running out of time, but for the subset of folks who are curious about the details, one challenge with the Kumaratunga et al. Functions is that they rely on both the growing temperature, so that's like acclimation, and the home temperature where a species is from, which incorporates more adaptation on longer timescales. But the atmosphere only gives one of those things to the land model. But when I experimented with different home temperatures, those details were kind of second order to the response to the growing temperature. They didn't make a huge difference. So it would take some more thought and some more work to implement that acclimation part globally. But for the purposes of this particular science question, it doesn't seem like it will be a huge hurdle. All right. So with that, I'd be really interested to discuss kind of the science question or modeling details with any of you. I know there are lots of folks on the call who have thought about these questions quite a bit, and I'll just leave up a few of these next steps I'm planning since I'm out of time.
Great, thank you, Claire. Very interesting and provocative. So yeah, questions. Or comments.
Sorry, Dave, I couldn't find my hand.
Yeah, no worries.
Great, Claire. Really interested to see that. If you're looking at the different stomatal models in, is this in Fates or CLM? I've just forgot.
It's in Fates.
Yeah. So in Fates, there's you've got a ballberry option and the Medlin option that Cherry just put in. And you'll start to see a divergence between those models in terms of the VPD effect at about 1.5 kPa. Which model were you using in these simulations?
So for the plots I showed just now, that was ballberry, just to kind of save you all from a million lines of different colors and line thicknesses or whatnot. But I've run it with both, and yeah, it does make a difference, and they start to diverge at higher VPD and higher temperatures. But the stomatal slope parameter, like the Medlin slope or the equivalent for ballberry, has a much bigger influence on the shape of the response curves. So
yeah, I think you're on the right lines with the G1, and then I think looking at the VC max would be good as well.
Yeah, absolutely. Thanks.
Cool.
Anyone else? Okay. Thank you, Claire. I think we will move on then. And if you have a further question, put it in the chat, or we can return to it in our discussion. So next up is you, Lee. So go ahead, you. Looks good. You're muted though.
Okay, yeah, that's good. Thank you. Yeah, today I'm for those who don't know me, I'm a postdoc working with Jim Randerson in UC Irvine. Today I'm gonna talking about the because we have learned a lot about the carbon fluxes, but today we are trying to talk about the carbon storage in the vegetation and also the tropical deforestation. So for this, sorry, let me check. There's something wrong with my slides. Okay, cool. So for global change, we know that climate change and land use change are two main risks to the tropical ecosystem. And we know the increase in CO2 will cause global to be warmer, and this will cause the ecosystem to generate carbon feedback to the system. And also the land use, such as the deforestation, also plays a very important role. So one essential task for us is to quantify the specific pathway in this. So in this framework of the climate carbon cycle feedback, we know there's a gamma quantifying the CO2-driven climate change. That is, the carbon will release more carbon to the atmosphere, and in response to the increase in CO2. But this gamma is driven only by the CO2-induced climate change, but also in the tropics, especially other climate change is driven by like the deforestation. So our question here is, does climate change associated with the land use change in the tropics yield a larger or smaller gamma? And so to answer this question, we should be aware of that one of the difficulties to quantify this feedback from associated with the land use change and land cover change is because there's very complex pathway for the land use in the climate carbon feedback framework. So for example, in the tropics, the land cover change, such as the deforestation, will cause the land to emitting more carbon to the atmosphere, and this will change the carbon cycle and feedback to the climate change. And finally, this will also exert influence to the terrestrial ecosystem. So our study is really want to focus on this tropical deforestation with the climate carbon cycle feedback. So previously, we know this pathway that the tropical deforestation will cause declined vegetation carbon storage, which will emit direct CO2 into the climate system. But at the other hand, the tropical deforestation has been long identified to generate biophysical impacts on the climate, which will cause the local climate to be drier and warmer. And this will also cause a potential decline in the vegetation carbon storage, which will cause indirect emissions to the climate system. So what we really want to do here is trying to quantify these indirect pathways here. So we have trying to leverage the existing CMIP6 experiments, that is the LUMIP experiment, which contains PI control simulations, and also there's a global deforestation experiments. We are trying to quantify the deforestation impacts on regional climate through subtracting the control by the global deforestation experiments. And also we have performed additional experiments trying to replicate the LUMIP experiments, but only perform the deforestation in the tropics. So just to verify the the regional deforestation effects. And also there's a chance for us to revisit the climate sensitivity of the vegetation carbon storage using a new waveform-based ESA CCI above ground biomass data. So this data is recently released for the year 2017, 2018, and has the potential to be more consistent with the ground plus data. So and also we will use this data to show how does the spatial sensitivity of the vegetation carbon to climate varies. What's the difference between the model and also the observations? So this figure shows the the multimodal mean simulated deforestation impacts on the annual mean precipitation change in the tropics, and you can see there's a in the LUMIP experiments, the tree cover generally decreased at a pretty large portion, and especially for the Amazon, there's about 44% loss in tree cover. In Congo, there's 38% loss. In the tropical Asia, the islands, there's like 30% loss in the tree cover. And the different models generally produced a consistent decline in the rainfall across these three regions. And also there's warming effects in this, specifically in the Amazon, in the Congo, and but not very obvious in the tropical Asia island. And you can see, because there's also deforestation in the extra tropical regions that will generate like remote impacts on the temperature outside of this basin. Especially you can see the Sahel region, there's a general cooling effects. We have replicated the LUMI experiments by replicating the deforestation only in the tropics. We have shown that these cooling area is actually caused not by the tropical deforestation, it's caused by the extratropical, mainly from the North Hemisphere deforestation. And after that, we will revisit the observational spatial climate sensitivity of the vegetation carbon both from the observations and from the CMIP6 PI control simulations. So we used all the pixels within the tropics, excluding pixels in the deserts. So we found that spatially the above ground biomass has very high sensitivity to the rainfall, and the temperature sensitivity is relatively smaller. And the CMIP6 PI control simulation, the spatial sensitivity has generally a very small magnitude of the sensitivity. So this is mainly due to there's a simulation bias compared to the observations. So you can see, especially in the tropics, with a very high fraction of intact forest, like in the Amazon, in the Congo, in the tropical Asia islands. Here, the ESA-CSI data, the waveform-based data has indicated pretty high above ground biomass than the CMIP6 mean values. And also noted that here the vegetation carbon on the right hand is the total vegetation carbon, which is implies that the above ground biomass simulated by the Earth system model is actually much smaller than the ESA-CSI biomass data. So that's the reason why spatially the CMIP6 based rainfall sensitivity is smaller than the observations. So by combining these two results, we have estimated that the tropical deforestation in the Amazon has generally caused extra carbon loss in the vegetation carbon in the Amazon, like by 6.8%, in the Congo 4.1%, and 0.3% in the tropical Asia islands. And also note there's a above ground biomass simulation bias in the model. So we have also corrected the absolute values of the biomass based on observation relationship between the biomass and the tree cover fraction in the tropics. So these values has been estimated like 6.8% loss. And also we have used this relationship trying to recalculate a new deforestation-driven climate carbon cycle feedback. So on the first row of this figure shows the typical CO2-driven climate carbon cycle feedback parameters, and on the bottom row there's the new gamma driven by the deforestation caused change in regional climate. So we can see this deforestation-driven climate change carbon cycle feedback parameters is actually a very large magnitude compared to this one. So from these results, we can actually learn that in the Amazon, deforestation-driven climate change will cause the intact forest to lose an additional 6.8% of their biomass as a consequence of decreasing rainfall. And also, especially for the REDD project, we know the carbon credits for avoided deforestation should be larger to account for the positive forest effects on the regional climate. And also, we know that the land use effect actually on rainfall would amplify the climate carbon cycle feedback in the tropics. So that's what I think so. And thanks for the team in CAR for the support of the simulation of Cheyenne. Thank you.
Great, thank you. Very nice, really interesting.
Yep.
Yeah, questions for you again. Raising hand in chat or
Josh, your hand up.
Yeah, so thanks. So nice talk. I might have missed it, but did you actually calculate like the cost, like in terms of dollars, or what was the cost aspect of it?
It's measured by the above ground vegetation carbon storage. Is the cost that we call this carbon cost is not measured by dollars. It's a kind of like we know the deforestation has many emissions quantified by the loss of vegetation carbon, but also we want to quantify what is the additional carbon cost of this deforestation effect through changes on regional climate. But I mean, this is a kind of like first step trying to give some like real credit to this, but it's that's our first attempt trying to this. Yeah.
Anybody else?
I have a question.
Sure.
Previously, we you and we were discussing this. There was the concern, right, from the idealized deforestation experiment that it was kind of deforesting from the inside of the Amazon out, rather than what would happen in the real world, which is from the edges. And so, can you comment at all on what you think the impact of that, a little bit unrealistic deforestation pattern is having on your?
Right. We actually have trying to use this, the deforestation about 40% and the relation with the rainfall. We have assumed that there is a linear relationship. So we trying to extrapolate this relationship to the realistic deforestation and trying to calculate some we call the biophysical carbon cost here, and we put in the table. And this has just finished in the manuscript. So in the draft, and we have kind of like I'm waiting for Jim on the comments of this draft, and we will soon be reach out to our co-authors. Actually, I want to mention that based on this relationship, the extra carbon cost is kind of like really small compared to the land use emissions in the current global carbon budget. Yeah, so. Which is kind of probably the reason for people to neglect this effect. Yeah.
And the lack of a precipitation response over the Indonesia is probably just because it's maritime and the land does not really have that big of an influence there.
Right, and we have replicated the LUMI experiments using CESM on Cheyenne. Actually, I have trying to plot the pixels between the tropical deforestation and the global deforestation in the tropical Asia islands. I think the results is really divergent. It implies that the rainfall effects in the tropical Asia island is heavily influenced by the remote effects of the deforestation in the extratropics. Yeah.
Okay. Anyone else? If not, then let's move on to our final presentation in this session by Jessica Needham.
Cool. Can you all see that?
Yeah.
Okay, great. So hi, everyone. I'm presenting today on...
There it is. Yep. It was delayed. Go ahead.
Great. Sorry. So I'm presenting today on trying to represent crown damage in fates. So individual tree mortality is this incredibly important process that shapes patterns of carbon storage and carbon turnover at the landscape scale. So properly representing the processes that lead to mortality is going to be really important for capturing how forests are going to respond to global change. And one really important predictor of mortality is crown damage. So this is a figure from a paper by Ariano et al. From 2 years ago, where they used structural equation modeling and to look at predictors of mortality. And they found that crown form, this proxy for crown damage, was the most important predictor of mortality for these trees in a rainforest in Borneo. So then we have this question of, is crown damage actually worth representing in vegetation models? If trees are ultimately going to die from crown damage, is it worth the computational cost of trying to track this damage versus just modeling final mortality rates? And we had kind of two hypotheses for why damage itself might matter for forest dynamics. So the first one is that the lags between environmental drivers and eventual mortality actually influence dynamics. So some of these trees can survive for years or even decades with really altered allometries, and they might be behaving quite differently to a healthy tree during that time in terms of growth rates, etc. So, so the actual damage itself might matter then for our estimates of biomass and also for GPP. And then the second hypothesis is that cumulative damage actually matters because it affects the final mortality rates. So by giving trees this kind of memory of previous stress, we can start to capture interactions between different environmental drivers of mortality and the effect of kind of cumulative stress over the tree's lifespan in a way that we might not be able to if we have a kind of threshold approach to mortality. So in this talk, I'm really focusing on the first of these hypotheses here. So I started off with this very kind of simplified representation of damage within FATES. So it's independent of any environmental drivers at this point. I just added this damage module kind of on top of existing mortality schemes. So we have a kind of representation of a FATES patch here. We have canopy cohorts with the light green and some understory cohorts in dark green here. And then we have the mortality of this large tree or this large cohort, and that leads to the creation of a new patch shown with the dotted line, and some of these understory trees move to the new patch. So then on top of that, I added this damage module. So the crowns of the surviving trees get reduced, and this is just a kind of a reduction in crown area and also in the kind of biomass of carbon pools that would be in the crown, so corresponding to branch fraction. And then the PPA scheme then promotes some of these understory cohorts so that total canopy area remains constant. So at the moment, I'm modeling damage kind of with these discrete classes. So at the moment, this is 5, but this number could be variable. So we have healthy trees and then 20, 40, 60, and 80% crown loss. And there's a single parameter that just sort of defines the fraction of a cohort that gets damaged each year. So in this example, that's 10%, and I'm assuming that that's constant and is independent of previous damage level. So every year, some fraction of the cohort just gets moved equally between these higher damage classes. So then the first question was, do damaged trees actually have higher mortality rates in these simulations? The idea would be that if you're reducing crowns, you're reducing the capacity for photosynthesis more than you're reducing respiration. And so trees should start to deplete their stored carbon, and this should lead to carbon starvation mortality. And we do see that to some extent. So this is cohort size, so dBH in centimeters against time. And each panel here is a different damage class. So there's healthy trees, and then 20, 40, 60, and 80% crown loss. And the intensity of the red here is annual carbon starvation mortality rate. So we do see an increase in carbon starvation mortality in these higher damage classes, but it's really kind of limited to these smaller size classes. So nothing above about 40 centimeters dBH is that affected by this damage. And then if this is just kind of all damage classes combined compared to the control, again, we see that it's not having a significant effect in these larger trees. So there's two kind of explanations for that. The first is that in the field, larger trees are not actually dying of carbon starvation when they're damaged. And the second is that somehow the representation of damage in FATES is not capturing the processes that would lead to carbon starvation in the field. So based on observations, I think that probably this first explanation is more likely. Annual damage and mortality surveys across 6 tropicals found of the trees that had reduced crowns in one census and were then dead by the next census, they were equally likely to die standing, broken, or uprooted. So this kind of suggests that there are multiple mechanisms that might be leading to eventual death in these damaged trees. Potentially they're more vulnerable to wind damage. Just as an example, if they were all dying of carbon starvation, we'd probably be more likely to see an increased proportion dying standing. So because I kind of wanted to be able to capture the effect of damage on mortality in larger trees, I introduced this new mortality term. And this acts kind of in addition to existing mortality within fates, and it's just a kind of additional mortality that increases with increasing damage. So that's kind of shown here. And then you can see the effect on size in this right-hand figure. So this again is cohort size through time. And now the red is showing this new damage mortality term. And you can see that mortality is starting to increase in some of these larger size classes. And with this new mortality term, we're sort of able to capture the observed relationship between damage and mortality that we see in field data. So this is just total mortality rate now against damage. And the green bars here are observations from Barro Colorado Island in Panama from these kind of annual mortality and damage surveys. And the orange here is the simulations in fates where we had damage turned on, but no additional mortality. And then the purple is with this additional mortality term. So you can see that with the additional mortality term, we kind of do a better job of capturing the relationship between damage and eventual mortality. So the question was whether lags between the onset of damage and eventual mortality actually matter for forest dynamics. So the first thing I looked at was growth rates. This is cohort size, dBH in centimeters again, through time. And now the intensity of the green is annual dBH increment. So you can see that growth rates are quite reduced, these trees that have reduced crowns. And at the plot scale, that leads to a reduction in both gross primary productivity and net primary productivity. But the effect is really more pronounced when we have these simulations that have the additional damage mortality term. So the orange, the green now is a control simulation in fates. The orange is just with this damage turned on, and then the purple is with the additional mortality. And you can see that the effect is much larger when we have this additional mortality term. In terms of carbon residence time, it's quite a similar story. So the control and then with just damage are not that dissimilar, if there's any difference really. But we do see a reduction in carbon residence time when we have this additional damage-related mortality term. We do see a difference though when we look at the size distributions of these simulations. So this is the number of plants per hectare per centimeter against size, and these are log axes. And this is in the canopy and in the understory. So if we start with the understory, you can see that there's much fewer large trees in the understory in these simulations where we have damage. And I think that's just because if you have reduced crown areas, then you can pack more trees into the canopy. So basically what's happening is that these smaller trees are being promoted into the canopy. And you can see that here, that in the canopy size distributions, we have a higher number of these kind of intermediate sizes compared to the control. And in terms of above ground biomass, there is this reduction in AGB in both simulations, but much more so with this additional mortality term. But the question was not really, does additional mortality matter? It was whether the lag between the kind of onset of damage and eventual mortality matters. And that lag is controlled by the fraction of trees that are damaged every time step. So we can look at that by calculating the residence time of cohorts in each damage class. So that's shown here. This is just the residence time of cohorts within the first damage class, so with 20% crown loss. And these are results from an ensemble where I was changing the fraction of trees that get damaged each year, and also the relationship between damage and eventual mortality. And what we see is that this residence time is really dependent on the fraction of trees that get damaged each year, kind of unsurprisingly. And so when there is a larger fraction of trees damaged every year, then trees have a lower residence time in each damage bin. So they're moving much more quickly between bins and then dying much more quickly as well. So we can look at what that means for forest kind of structure and function. So this is now showing the same ensembles, but we're seeing above ground biomass and carbon residence time. And if we look at this top row, so where the cohorts had the shortest residence time in each damage bin, so where they were moving most quickly towards mortality. These are the simulations where we have the lowest above ground biomass and the lowest carbon residence time. So it kind of looks like these results are suggesting that it isn't the damage so much that's important as the kind of additional mortality. If trees are kind of, if we're just increasing the turnover of the forest by kind of moving trees quickly through these damage classes to eventual mortality, that's what's having the biggest effect, not really the fact that they're that they have these altered allometries for long time periods. So to conclude, this damage module, it provides us with new capabilities for hypothesis testing. Combined with observations, it kind of suggests that carbon starvation alone is not what's killing these larger damaged trees in the field. And in the case of this idealized forest, the effect of damage on stand structure is mostly due to the altered mortality rather than the damage itself. But I think as we start to add mechanistic drivers of damage and we test the effect of cumulative stress and the interactions of these different drivers of mortality, then we might start to see that the damage itself becomes important, but that's for future work. Thank you.
Thank you, very nice. Questions?
We've got, here, Jackie, I'll just let you ask your question.
Sure. That was really nice, Jesse. So I had a question about the observations. You had that histogram in class 3 was like lots of death in the observations. And so I was curious what was happening there. And then beyond that, I wanted to ask, like, I think this will be really interesting to look at how a damaged tree is more susceptible to other sorts of damage, like wind damage or fire damage or other things. And so have you thought about those interactions or started testing any of them? So 2 questions, yeah. Sorry.
Great questions, thank you. So the first one, I'm not entirely sure why mortality is higher in that kind of intermediate damage class. I would have expected it to be like a more increasing relationship. It could just be a sample size thing. There's only 5 years worth of observations at this point, and the sample size is fairly small. I think it's like a 2 hectare area maybe for BCI. So yeah, I don't know if that would change as we kind of get more observations. For your second question, I have not started testing any of this yet. I think there will be an interaction, and I don't know if it will kind of emerge from the way that Fates is kind of already structured, or if that's something that would kind of need to be implemented sort of additionally. So at the moment, the only mechanism in Fates that was leading to additional mortality was this carbon starvation. So I don't know if we were thinking about sort of wind throws, we would need to kind of account for tree architecture, and I don't yet know the details of kind of how that would be done.
Thanks. We have a couple questions from Joshua and Jennifer, actually both asking about how you change the crown allometry for the damage, and then also how you then enforced it, how you enforced trees from staying in the new crown allometry.
Yeah, so I just added after, so every kind of, I basically just I changed the actual allometry functions within Fates, and they get kind of forced every time that a crown area is calculated. If a tree is in a higher damage class, it gets recalculated for that damage class. So it's there were simulations where I was kind of allowing things to recover by comparing leaf biomass to sort of target leaf biomass, but those simulations are a bit wonky. So here I'm just showing kind of non-recovery simulations. Does that kind of answer your question?
Thumbs up from Joshua.
Yeah, I think from me, it does. So the trees were always still able to stay on allometry. You said when after a tree was damaged, then it would recalculate the allometry function, I think you said, right? So it always stayed on allometry?
No, so it was it was being kind of like forced off allometry constantly. So I would like change what the target allometry for the tree should be based on its damage class.
Okay. Thanks. Yes.
Sorry, I didn't explain that too well.
No, I was a little confused with on and off allometry. Got it.
Anybody else? Dave?
So I'm trying to understand with how realistic these damages are. So what's causing them. The way I was interpreting it, what you're showing is that it's like a tree in a relatively intact forest gets damaged for some reason, or I guess maybe is that what's going on maybe in the tropics, so that or is it more like a whole bunch of trees in an area kind of clear out a space, and is there any difference then in the impact of treating it like one tree getting damaged versus a whole hectare of trees?
Yeah, that's a good question. So at the moment, it's kind of it's more like one tree in a relatively intact forest being damaged, and I guess that would be more like maybe kind of insect infestation or like some pathogen that's causing just like one individual to be affected when its neighbors are not. I think you could apply this in a more kind of to sort of replicate more what happens when we have like a cyclone or something. I guess the difference would be sort of how you handle the kind of canopy organization. At the moment, I didn't change any of the PPA code, so we just get this promotion of understory trees to the canopy. I think if you wanted to have like a more extreme damage where you were creating light gaps, that part of the code might need to change.
So just want to open it up here to questions or comments on any of the previous presentations. We're in this discussion period. So not just restricting to questions for Jesse, although continue. Or any general comments that anyone wants to make. If there's nothing, Will, do we want to move on to lunch? Or
Joshua has his hand up.
Yeah, so this is going to, I believe, our first presenter, Dr. Solis. I hope I'm pronouncing your name properly. I was trying to understand sort of your final point of your conclusions, and was trying to understand when you were talking about the intraspecific changes or differences that you were observing across your sites, whether you were making new you were modifying, you were using, changing the PFT composition among the default PFTs that are available, or whether you were modifying PFT parameters in order to capture that variability. And if you could just follow up on that.
Hi. I mean, so if I understood correctly, so the point that you're making is, so what's basically the idea behind this looking at intraspecific, interspecific variability within the eddy covariance footprint, right? So the idea is try with this point scale simulation to mimic each plant species individually, right? So instead of having one PFT, so treating this different species as an individual PFT, that's basically the long-term goal. So that's why we are start looking at the variability of the intraspecific plant within the PFT, and then we're going to look also in the intraspecific.
Just a follow-up, for these sites, how many species, how complex are these forests that you're looking at?
Yeah, in the first slide, you see we have 2 sites. We have just one species within the eddy covariance footprint, and then in the other remaining 4, we have multiple tree species. So in this, the idea would be then using this plant parameterization to mimic multiple PFTs within the same grid cell, but where the multiple PFT are actually the different tree species that we have, right? That's pretty much, and then to see how this variability in these species results in the variability in the ET response at the grid cell.
Thank you. That helps clear it up a lot.
Great. Any other questions for any of the presenters or thoughts on the talks that we heard this second session of the morning? Let's be back at 1:15 Mountain Time, so a little more than an hour for lunch or stretch or walk.
Will, are you sure?
Yep.
1:15?
Did I get that wrong? Oh, it's 1.
1, yeah.
Oh, thanks. So less than an hour then.
Yeah.
Yep. All right.
Cool.
See everyone shortly.
give another minute. Will, just people coming back from lunch.
Sounds good. Yeah, well, folks are logging on. Elizabeth mentioned in the chat that just a reminder to send her a copy of your slides if you presented, so she can post them on the website. Her email is fair@ucar.edu. And she's been stripping out any presenter notes that are in there, and she'll just post a PDF of the slides themselves. So.
All right, should we get started?
Yep.
Okay, so I think first in this session is Jackie to give us an update on firework, I think. So go ahead, Jackie.
Yep. Thank you. Okay. Are you seeing my presentation?
Yep.
Okay, great. So my name is Jackie Schumann. I'll be talking about fire behavior and effects with the FATES model. And I want to thank my co-authors and collaborators, in particular, Charlie Coven. He helped me figure out some things that have been persistent. So thank you, Charlie. I appreciate it. Okay. Jeez. I cannot move forward. Why not? Sorry. Oh, there we go. So these are active fire counts for yesterday. If we include more time over the past 4 weeks, you can see that we have a very broad spatial coverage, even just within the past month. If we look at a longer period of time, the average burned fraction from 1997 to 2014, you can see broad patterns of the fire regimes that result globally. And so in particular, the areas across the tropics get consistently high amounts of burned fractions over long periods of time. Sorry. Historically, we have seen increases in fire danger. So shown here on the left is the change in fire weather season length for the historical period. And then on the right, this is a recent analysis that came out with the CESM1 large ensemble that looks at the change or the possibility of exceeding extreme fire risk. So a value over of 1 for the figure on the right indicates extreme fire risk. And so you can see that the increase of risk for more frequent and severe fires has already happened historically, and then it's projected to continue to happen. So, sorry. And so for the tropics in particular, this is important because we have large carbon stores in the tropical forests and a conversion of these forests to something that is less carbon rich, like grasses or sparse tree cover, is going to emit a large carbon source to the atmosphere. So we really need a model that can capture these feedbacks, and to that end, capture the feedbacks between vegetation structure and fire risk. So to do that, we've adapted Spitfire to work in the FATES framework. And so FATES is the functionally assembled terrestrial ecosystem simulator. It's being developed as part of a DOE project, the NG Tropics. And so FATES is a module that runs within a host land model. It replaces the traditional big leaf processes with more realistic vegetation. This allows us to capture plant physiology, competition, ecosystem assembly, as well as ultimately vegetation distribution. And so Spitfire operates within the FATES framework. It is one of the mortality drivers. And so what you have is fire weather and ignition events. For this work, I'm using a spatially and temporally varying lightning ignition data set. And so fire weather and ignitions come in, you evaluate your fuels, how much fuel do you have, whether or not it can combust, and then depending on that amount of combustion, you calculate fire behavior. So you calculate fire intensity. With the calculation of fire intensity, you evaluate fire intensity and duration. You evaluate vegetation mortality. From that mortality, you then determine subsequent vegetation regrowth. Fire is evaluated on a daily time step for individual patches. And so within a grid cell, you can have subgrid heterogeneity. And so if we look specifically at mortality, tree mortality is different. And so we have trees are killed by fire due to fire intensity and duration. Scorch height determines how much of the canopy might be damaged by fire. And then the trees have the possibility for bark damage, and this varies with bark thickness. So as the trees get taller, they accumulate more bark, which offers them more protection from fire. The ultimate accumulation of bark, it depends on the specific tree. And so some trees are better at accumulating bark than others, and this is supported within the literature. Grasses do not have protection from fire, and they burn when you have a fire. And then fates, when a fire comes through, due to this differential survival of trees, you have the possibility of retaining fire-affected canopy structure, which means you're going to have different fire behavior at your next time step. We've had some notable updates. In particular, Charlie found a typo. So the original Spitfire implementation used a Canadian reference from 1992. But there was a typo, and that was corrected in 2009, but all of the Spitfire variants had the typo, including fates, but we recently fixed that. So thank you, Charlie. So I've been looking at forest savanna bistability. And so within the figure at the top, the forest is considered stable in the areas shown in green, and then the areas shown in red are low tree cover or savanna. And whether you have this forested area versus low tree cover is connected to climate, the number of dry months, fire frequency, and vegetation traits. And so what we wanted to look at with fates was whether or not we could capture this separation. Within these savanna, and so I'm focusing specifically on South America. And so bark thickness is known as a vulnerability indicator for trees. It's closely connected with burned area. And so, but this evolves over a very long period of time. Within South America, this is a good place to look at the difference in bark thickness. Forest trees are much thinner than the savanna trees. And these infrequently burned areas where we have high carbon stores are considered vulnerable for future changes in fire. And so I have 1 degree simulations with and without fire using the GSWP3 dataset, as I said, spatially and temporally varying lightning. And the results are an average across the final 10 years of the simulation. And so for this, we have 3 PFTs that compete within a grid cell. We have a moist tropical tree, generic moist tropical tree that's considered vulnerable to fire, and a dry tropical tree that's considered fire tolerant or resistant, and C4 grasses. And so these results are updated with the new simulations. And so what we see at a minimum, fire acts to limit tree extent. And so the simulations without fire shown on the far left, a value of 1 indicates 100% of the canopy is trees. And so you can see in the middle that the tree coverage is limited by the presence of fire compared to observations from Landsat. And so if we look specifically at those forests and compare them to observations of biomass, you can see that the forested areas are high biomass, a little bit excessively high. In particular, we have, and then we have this presence of these Atlantic forests. These simulations do not have land cover land use change, so it's not completely surprising that we have these forests here, but they're quite robust. So I need to adjust the parameterization. If we look at precipitation, you can see that the areas where we have forest correspond to areas where we have higher precipitation. And this is in line with the expectation for low tree cover. But we're getting no tree cover, so we might be doing too good of a job of making this a binary system. If we look at what's happening with the fire regime at that location, you can see that in the middle we have burned fraction, and then on the right we have observations of burned fraction. The warmer colors indicate more burning. And so you can see that the areas where we have higher burning, we have a decrease in the amount of trees. If we look at, and so this area where we have high burning is an area where you have a strong presence of grasses. And so this is this fire feedback where the presence of grasses promotes more fire, and it continues to decrease the amount of trees. The fire that we have across South America is generally low intensity fire. And so the figure on the left is fire intensity. So the energy of these fires below 2000 kilowatts per meter are considered, you can effectively manage these fires with ground crews. So they're not inconsequential, but they're lower intensity fires. So they're not going to burn up your whole canopy. If we look at the seasonal cycle within the observations, you can see that there is variation in the fires throughout the year. And if we pull out the fire season, so from July through November, and compare that to what's happening in the simulation, you can see that spatially we're getting the spatial pattern, but again, within those areas dominated by grasses, once we transition into the dry months, you can see that Fates is showing repeat burning, and where the observations are showing a lot of burning, but not necessarily at the degree Fates is. But again, these are low intensity fires. And so I think there is a bit of a mismatch between what's happening in the observations and Fates, but I do think Fates is a bit excessive with its grass burning here. And so I need to go in and investigate what's going on with that. But the interesting thing about these latest results for me is if we look at the vegetation traits, and so specifically size, structure, and bark thickness. And so this is looking specifically at fire mortality. And so the figures on the top row are the thin barked trees, and then below them are the thick barked trees with the small size classes on the left and the larger size classes on the right. And so what you can see is that all of the small trees from both types experience fire mortality, but the thick bark tree, as it gets taller, experiences much more less fire mortality than the thin barked tree. So the expectation moving forward is to look at a similar set of simulations with future climate scenarios to see the differences spatially. Because we know that the thin barked trees are predominant in this stable forested area of South America. And so with that, I'll finish and just leave this up here. And so we're capturing the forest grass dichotomy for South America. We have, high biomass, and then a little bit of excess fire for the grass areas. And so we have this increased fire feedback dependent on fuels and climate. And then with the trees, specifically the tree size and bark do matter for fire survival, which is what we have in reality and we're now capturing in the model. So thank you.
Great, thanks, Jackie. We do have some time for some questions.
I guess in the chat, Stephanie Falk is asking about natural ignitions versus anthropogenic ignitions and what you're using here for these simulations.
Okay, that's a good question. So these simulations are just natural ignitions. I have not implemented anthropogenic ignitions. Will,
you've got your hand up.
Yeah, I was curious in Fates, what's the trade-off for having thick versus thin bark? Do you get that? I don't remember where the observation was from, but the observation of thicker barked trees and more fire-prone areas. Like, do you get that shift in relative abundance with Fates?
I I haven't, so I was just, so the trade-off, the thicker barked trees are generally, they have lower biomass, they have a different canopy. I haven't looked at whether or not FATES is able to separate the actual location of where those trees are, but but that's my next step, is to look at specifically a trade-off between a thin bark tree versus a thick bark tree. In this simulation, the thick bark trees had an advantage in a number of ways, and so it wasn't a good test to capture that difference.
Cool. Thanks.
Dave?
Yeah, I'm wondering, you have this potential that it's overdoing the grass fires. And I'm wondering what in the real world is like preventing all the grasses from burning up that could be missing or in FATES.
So within FATES, we have multiple fuel classes, and we have dead leaves as well as live grass are a specific fuel class. And right now their fuel moisture content varies as a component of their surface area and the surrounding climate. In reality, grasses are extremely complicated as a fuel. And so grass curing is a thing that determines whether or not they're available for burning. And that's something that we don't have in the model right now. There are parameterizations out there that we could implement. And given this overabundance of grass burning, it's possible that we need that for South America. It's not in there right now. So it's a very simplistic representation of grass as a fuel. And so it's essentially how much water is inside the grass that's available to burn. Right now, we're just looking at surface area to volume.
Thanks. Renato?
Hi, Jackie. Great talk. My question goes towards the anthropogenic activity. As we know, all the fires in the Amazon, this past year has been, it's anthropogenic. So I would like to know if you have I know it's not implemented right now, but if you have at least an idea, or we can do a mental exercise here together, thinking about how would we implement then anthropogenic fires that represent a huge part of the fires in the Amazon and the impact on the carbon cycle in that area.
Sure. So there are methods for representing anthropogenic ignitions. It's just I haven't implemented it within FATES, and there are plans to do that. And so one of those is you can implement it at a regional scale, or it depends on the degree of specificity that you want. And so a lot of these deal with GDP as well as fire suppression within an area. That's the implementation that's in CLM. And so we'll probably start with something similar within FATES. And so what it would be is it would increase the amount of ignitions consistently across South America based on GDP and fire suppression measures. And so what you would expect to see is an overall increase in ignitions spatially, whereas the lightning data set has spatial and temporal variation. Does that answer your question, Renato? It's a good question, and it's a good point. And then the other point that isn't included here would be ignitions due to logging activities. And so that's something that you could implement more specifically at a location with the inclusion of logging.
Yeah, it does answer. Thank you very much. I think the idea of trying to represent that following GDP it's a good way to do that. I'm thinking here if we could use some sort of satellite data, and even going a little sci-fi here, using some sort of legislation, because we can assume GDP is a good proxy for if a country burns more or less, but legislation also plays an important role. So it would be cool to see CLM merging with the law and humanities in a sense.
That's a good idea. I like that idea.
Nice. That's a nice dream. So there is a comment from Rosie, but maybe we should return to that in the discussion. So let's move on to the next presentation, which is by Adriana. So take it away. I'm pretty sure it's Adriana, right? Yes, good.
Hi, thanks.
see my screen? Yep. Okay, great. Yeah, so I'm going to talk a little, sort of still on fire, but shifting gears in terms of models a little bit. So wildfire is a dominant driver of ecosystem dynamics in the boreal forest, which has impacts on below ground carbon storage and above ground carbon storage, vegetation structure, species composition, soil characteristics, permafrost dynamics, and energy and water cycling. And in particular, the boreal forest, the fire severity and subsequent depth of burn leads to direct impacts on post-fire regeneration. So with higher severity and greater depths of burn leading to more deciduous recruitment following fires, and whereas a deeper post-fire organic layer depth often results in coniferous recruitment following fire. And so in the North American boreal forest, this can lead to lasting legacies of vegetation type through interactions with vegetation and soil characteristics. So it's clear that these linkages between vegetation dynamics, soil characteristics, and disturbances are highly important in this region and thus are important to include in simulation efforts for these forests. So the UVA-FME model is an individual tree-based forest gap model, which simulates individual tree establishment, growth, and death on independent patches of a forested landscape. And so trees grow annually via diameter increment growth in response to external factors like sunlight and temperature, precipitation and soil moisture, and soil nutrients. And then trees compete with one another for resources and can die through low growth or via disturbances. And then new trees are regenerated based on environmental conditions and species-specific tolerances. And so this model has been updated for use in the North American boreal zone with the addition of permafrost dynamics, shrub and moss growth forms, and process-based fire simulation. And so the model has been found to reliably predict forest characteristics when compared to inventory data. So here on the left, we can see average total basal area for about 900 sites across Canada and Alaska, grouped by forest type and ecoregion. And so here in general, the modeled and measured basal areas agree. Model output on abiotic and biotic vegetation drivers also compare well to field observations. So on the right, for those same 900 sites, we can see inventory versus modeled soil organic layer depth. And so not only is UVA-FME able to reliably produce forest dynamics and characteristics, but it can also simulate the underlying vegetation drivers that influence such dynamics. And so the model has been updated to include Spitfire type fire simulation with the rate of spread and fire intensity based on a combination of fire weather and lightning strike frequency, as well as fuel loading, geometry, and moisture. And so I modified the original Spitfire equations and code to accommodate more boreal specific processes and to better accommodate the gap model structure and scale of UVA-FME. So for example, fuel litter is added annually to litter pools, including deciduous and coniferous leaf litter, twigs and moss for 1 hour fuels, small and large branches, as well as live shrubs and trees less than 6 feet in height. And then in the boreal zone, dead fuel decays from fresh to fibric to humic. And in this version of the model, we update the geometry of the litter pools as they decay to simulate this change in bulk density and surface area to volume ratio as the litter decays. So I also added passive torching and active crown fires to this version of the fire model. So under passive torching, fire intensity is sufficient to ignite individual tree crowns, but does not travel across the canopy. And so the critical surface intensity required for passive torching is based on the canopy base height of the stand, with higher canopy base heights requiring higher intense fires. And then in active crown fires, intensity is high enough for fires to spread across the crown. And so this minimum intensity is based on canopy bulk density, with less dense canopies requiring higher intensity fires. And so here on the left, we can see UVA-FME simulated species-specific biomass with the different colors representing different species before and following a high-intensity fire at stand age 100. And so we can see that the species composition does shift slightly following the fire, with more black spruce and jack pine biomass in the blues, whose serotinous cones allow for rapid colonization following fire. And then on the right, we can see the change in the organic layer and moss depth for the same simulation. So I added smoldering combustion of the organic layer to this version of the model based on fire residence time and soil moisture. And so we can see the burning of the organic and moss layer, then with eventual regrowth of these layers following the fire. And to validate these updates, I compared simulated above and below ground combustion to about 300 observations across Canada and Alaska. And so here I forced a fire to occur at the stand age and the day of burn from the observational data set. And then climate in the model is based on input historical distributions. So we just pull from a mean and standard deviation to create weather data each year. So in order to avoid sort of strangeness with maybe lots of rain randomly occurring on the day of the fire, I also forced the model with the wind speed and fire weather for the day of the burn from the nearest weather station. And so here we can see comparisons of observed in purple and modeled in green above ground combustion on the left and below ground combustion on the right, again grouped by ecoregion. And so we can see that the model is producing this combustion fairly well, and it also produces variation in the above ground combustion by ecoregion. So broadly, it seems that this updated model is performing well within the North American boreal zone. So it's predicted that fuel flammability will increase in the future with increasing temperatures and drying conditions. And then models also predict an increase in deciduous fraction with climate change for the boreal zone. And so this sort of throws somewhat of a wrench in our increasing flammability projection, at least for the boreal zone, because deciduous litter is in general less flammable than coniferous litter due to both its geometry and the overall total loading for coniferous versus deciduous stands. So if our original prediction for flammability were to hold, this would mean that fuel drying is high enough to outweigh this shift in litter type. However, if deciduous fraction is more important, we might expect flammability to level off or even decrease over time. So we can use a model like UVFME to investigate questions like this. So to investigate these interactions, I simulated the model at the 300 combustion sites forced with RCP 4.5 and 8.5 climate change out to 2100. And so here on the left, we can see above ground biomass for RCP 4.5 in blue and 8.5 in red for Alaska and the Northwest Territories. And so we can see for RCP 4.5, we did get some declines in biomass, but overall not much change. But for RCP 8.5, we did see declines in biomass for both regions. And then on the right, we can see deciduous fraction. So for Alaska, we had increases in deciduous fraction for both scenarios, whereas deciduous fraction only increased for RCP 8.5 in the Northwest Territories. Okay, so what's going on with the fire regime? So here on the left are distributions of fire intensity for the different scenarios, and then on the right is fire return interval. So we can see that for both regions, fire intensity declined and fire return interval increased with climate change. So meaning that fires were getting less intense and less frequent as climate change progressed. And then we can also see declines in total fuel loading on the left, as well as moss biomass on the right. So here it seems that deciduous fraction was more important than fuel drying in these simulations, as the fuel amount declined so much that we couldn't really sustain intense fires. And so it does seem that we are seeing this interaction between fire and climate change simulated by this model, with a potential change in this legacy lock on vegetation type with climate change, where high severity fires under climate change may lead to a shift from a coniferous stand to a deciduous one. So how can we use this detailed model to inform maybe coarser scale models and like FATES? So there are a lot of shared similarities between a model like UVFME and FATES that make them ideal candidates for comparison. They both consider vegetation structure and detailed vegetation ecosystem connections. They're also both based on sort of first principles of ecology. However, there are differences that make comparisons interesting. So UVFME is an individual-based model, whereas FATES simulates cohorts. UVFME tree growth is based on annual diameter increment growth, whereas FATES simulates daily and sub-daily photosynthesis and allocation. And then UVFME patches are run independently and all from bare ground, whereas which is different from FATES patch aggregation and creation dynamics. And then the soil column for UVFME is also independent for each plot, whereas FATES shares the soil column across patches. And finally, UVFME contains fairly few parameters in comparison to FATES, which makes it slightly easier to get up and running in new locations with new species. So Jackie Schumann and I have been working on comparing FATES and UVFME at sites in Canada to see if there are ways to benchmark FATES with UVFME. So for this project, we forced UVFME with FATES environmental conditions. So this way the differences in modeled and vegetation dynamics would be due to the vegetation processes and interactions rather than differences in, say, soil moisture simulation. And so for this, we forced a number of driver variables like temperature, precipitation, active layer thickness, and soil moisture. And so here's a comparison of FATES output at a black spruce site in the Northwest Territories. So for FATES, Jackie ran a 200-year spin up and then logged the stand. So I just sort of reset it to 0. And then for UVFME, we just ran it from bare ground. So we can see that actually the models compare really well in terms of biomass and species composition. However, if we look a little further, we can see that there are differences in what limits growth for cohorts and trees at different sizes or different stand ages. So on the left, we can see the factors that went into mortality for trees and cohorts of different size classes, and for different stand ages for UVFME on the right and FATES on the left. So for UVFME, we can see the changing limiting factors as trees age and as the stands age, but with small trees in the older stand mostly completely limited by shade, whereas larger trees are mostly limited by temperature, nutrients, and drought. However, for FATES, the mortality causes seem more static across the size classes and stand ages. And if we take away termination mortality and impact mortality, the static rate seems even more apparent. And so this has implications for size structure of these simulated stands. So here is looking at size structure for UVFME and FATES. And we can see that even though the biomass was very similar for the two models, the size structure is quite different. So, the small trees for FATES are on orders of magnitude larger than for UVFME. And then if we zoom into the plot, we can see that the size structure for UVFME changes with stand age, whereas it remains, somewhat static for FATES. And so here's the same type of comparison for another site, which has permafrost near the surface. And so here for FATES, we're getting some strange episodic mortality events, which may be due to permafrost. But again, we can see that the mortality causes seem somewhat static. And so these results are giving us a path forward for diagnosing issues that arise with FATES and for improving the performance of both models in this region. So in conclusion, we can use highly specific gap models like UVFME as somewhat of a data surrogate across a broad region. So data needs for FATES validation can be prohibitive. And so being able to compare FATES output to a model like UVFME for quick comparisons across a large region could speed testing with FATES. And then because FATES and UVFME are so similar, we can use comparisons to highlight specific processes that drive vegetation dynamics and that may need improvement. And then in general, the consideration of structure allows for detailed vegetation, climate, soil feedbacks, and for consideration of important processes such as seed rain or forest management. And with that, I'd like to thank my funding sources and collaborators. And I will take any questions if we have time.
Yep, we have time. Thank you. That was excellent. So you're proposing the EVA for me is like a LES.
Yeah, I think, it produces, obviously it's not as specific in terms of it doesn't get, CO2 and these sort of like really detailed radiative changes. But I think, on the whole, it's shown to be very robust in terms of simulating forest dynamics.
Yes, so questions.
I like your Twitter handle.
Thank you.
Jackie, you've got your hand up?
Oh, I was just, if there aren't any questions, Adriana and I are soliciting feedback on if anyone has ideas on what's going on in this permafrost site. But Katie has a question, so yeah.
Thanks. Well, I was going to ask about the other site actually, because it also seemed like there was some variability in FATES in the biomass that wasn't present. Yeah, exactly. So I was wondering about that sort of decadal variability possibly in FATES that's not present in the other model.
Yeah, so I think that's due to the forcing data. So we're using GLDAS 2000 to 2018. So I think we're getting these sort of signals as we're recycling the climate data. I'm going to look into the mortality over time and see like what's happening, but maybe Jackie has other comments on that as well.
Yeah, I think the climate signal is an important piece. There was also, the soil moisture is an important component. But yeah, we need to dig more into it. And so even though we had this episodic behavior with this site, it didn't cause like catastrophic failures, but there could be a similar mechanism to the permafrost site and this site. It's a valid point.
Thanks.
Gordon?
Adriana, great talk. As you know, I'm a fan of gap models, but I wanted to explore more your thoughts on this idea of the CLM and land surface models doing growth based on photosynthesis that then gets sort of scaled up into biomass pools that then through allocation sort of gets allocated and they grow that way, versus a gap model, which is the diameter growth. And then that is sort of scaled based on these empirical site factors.
Yeah.
And those site factors are really easy to sort of work with because they can get they're empirically based. And I think, the permafrost example is a really nice one because you can have a permafrost factor in a gap model, but in a model like CLM, it's all sort of based on soil temperature or soil moisture as it affects photosynthesis. So I wonder if you could like comment on those two different approaches.
Yeah, I think, like you said, I think, with FATES, it's definitely trying to be more process-based and less empirical with its allocation and photosynthesis schemes. And I think, there's a benefit to that in terms of trying to get at, the true understanding of how trees function. And especially if we're looking to the future, these empirical equations that we develop may not hold in the future. But, with UVFME, I think we're also, by using these empirical equations that are built off of, long-term, studies of forests, we're sort of like baking in all the things that we don't understand into this empirical equation. So we kind of can assume that, okay, we're getting the right answer because here's the data and we've, sort of run a regression. And so I think it allows for faster sort of understanding of why things are happening and like getting it to work. Yeah. So I think there's some, I think like using the two in combination, I think can lead to improvements for, for both models and especially for FATES if we, have this really highly process-based allocation and photosynthesis scheme that is corresponding with what we see, under historical conditions compared to the forest dynamics that we get out of a gap model. I think that could give us a lot of confidence for, future conditions or unknown conditions.
Thanks. All right, Josh, for the last question.
Yeah, great presentation as always, Adriana.
Thanks.
So you showed, and you talked about this a bit, but these differences between the results of FATES and UVFME, and obviously the inherent differences in the how the models works. But you kind of set it up to say like, like what's next? Like how do you take these differences in the results, and maybe they're related to the processes, and what's next? Do you alter CLM or do you alter FATES? Or like, I just wanted to, it wasn't very clear to me like explicitly what happened next.
Yeah, I mean, I think both, we can use the model to parameterize FATES better or UVFME to parameterize FATES better. I think, we can also investigate by turning on and off these different processes that are governing growth. Like, so permafrost, we found that maybe that's a huge issue and we need to investigate how are we implementing how permafrost affects tree, photosynthesis in terms of, moisture stress, because that can be a thing, but also just freezing and, maybe anaerobic conditions for water logging. And I think by turning on and off these processes in different models, we can identify where we may need to make structural changes in FATES that would improve the overall forest dynamics. don't know if that was vague enough for you, but
let's move on. Thanks a lot, Adriana. We can come back to this if we have time left for discussion. So the next presentation is by Arshdeep Singh, although I think Arshdeep Singh, though Sanjeev Kumar is going to present for him. So Sanjeev, go ahead and share your screen if that works.
Yeah. Thank you, Deb. You can see my screen.
Correct.
Okay, very good. Yeah, I'm presenting on behalf of my student. He's visiting his hometown and it's very late in the night, so in his hometown. So here we'll be shifting a little bit gear to the land use change. We'll be looking into the biophysical impact of the land use change on the temperature. We know from the previous assessment, particularly CMF5 or the lucid, that land use change impacts were quite uncertain in the climate model, and we thought like it kind of improved, so we'll see the results there. So as you see in these graphics here, on the top panel, you see the presented land use, land cover change. That's crop cover change mostly occurred in the Midwest United States going into some part of the Canada. Then there is a European region where the crop cover has increased. Then there is India in terms of Northern Hemisphere. Southern Hemisphere, not much change in the present climate. This all are compared with the pre-industrial climate. So we expect to see some of the impact on the temperatures due to land use change, and particularly the CMF6 and the LUMIP experiment allowed us to investigate this issue in little more detail that was possible compared with the previous version of the models. Then going into the future, what we see the Northern Hemisphere the crop cover change is not much expanding in terms of the area. Also, there is some suggestion of intensification. If you look into the India region, it's getting more color intense. Similarly, like if anything is happening in either North America or Europe, it's somewhat shrinking. But one of the most interesting area in terms of the future land use cover change is the Southern Hemisphere, both Africa and South America, where it is showing increase in the crop cover. This context is important because when we'll discuss how does the land use cover change impact the temperature in the future climate. So since the land use cover change is not increasing either in the North America or the Europe, so expectation would be like the temperature would not change much compared to the present day climate. There have been this has remained an active research area for at least last one decade or so. So some of the very good literature between 2015 to 2020 came from the German group led by Julia Pongrage, and they developed a very detailed methodology how to divide the total impact of land use change between local and non-local. And one thing that I wanted to emphasize here is if you look into the mid to high latitude range, when we see the total impact, that is stronger cooling, and when we only do the local impact, it's a smaller cooling effect. So they have a series of 2 or 3 papers describing their methodology. And their methodology where the idealized deforestation experiment and its fully coupled simulation, and also pre-industrial CO2. So this was the expected result if we go into the local impact, somewhat magnitude of the land use change impact on temperature will decrease. So we wanted to investigate some of these issues using the CMAP6 and the LUMIP model. So what I will be showing you the result today is a analysis from 5 LUMIP models. Those were available at some point of the time last year for the analysis presented here. So that would be a direct method. Direct method is you take the control run, means transient run, and then there is a no LU run. Where the land use change has been kept to the pre-industrial level. So if we take these difference, that will give the total impact, local versus non-local. Then back in 2013, I published a paper in JGR where we developed a methodology to do the local impact. And it's basically that's how you do in the observation, you compare to area of land use change and no land use change, and assess the difference or assign the difference between these two impact region to the land use change impact. Another advantage of this local methodology is there is an assumption that if there is a large scale impact, that would be same in the adjacent area, so that will cancel it out. So this is what would be called the K13 method, and this is a direct method coming from the LUMIP experiment. In the K13 method, we would not need that no land use experiment. So here is a comparison of the land use change impact on the temperature. This is a figure only for the North America. You see the direct method on the left panel and the K13 method on the right panel. What this figure is showing, what is impact on the temperature in this blue bar, and then what are the different energy balance component, and the error bar is also shown. If error bar crosses the zero line, then we'll say the impact is not statistically significant. So at least in the CMAP6, one thing we are finding that when we do the multi-model average, the 5-model average, there is a cooling effect due to land use change in the North America land use change region. And it doesn't cross the zero line. That means the result is statistically significant. When if you can look into some of the energy balance component, and almost all the 4 energy balance component except for the latent heat flux is, these 3 are not statistically significant. It looks like there is a statistically significant decrease in the latent heat flux due to land use change. Compared to the K13 method, yes, we get a reduction in the magnitude of the land use change impact as expected, but the impact remains statistically significant in this region. But we also see some of the energy impact, that energy balance impact, that were not very clean in the direct method has become clean, and now you see there is a reduction in net short wave as we expected from the higher surface albedo in this case. So we think that K13 method gives you somewhat cleaner result because it takes out the non-local effect. Moving on, this is what in terms of global looks like direct method. So the cooling impact, at least in the mid to high latitude region, there are some exceptions when we go to the low latitude region like India or some part of the Sahel, but most of those opposite sign of the impact are not statistically significant. When we in the direct method, when we do the K13 method, it is almost everywhere in the Northern Hemisphere. It's cooling impact, both Northern America, Europe, India, and some part of the Sahel. Magnitude becomes in the direct method is 0.14 with uncertainty plus minus 0.13, and it gets reduced in the K13 method. So we had a method. Now we know it works reasonably well, at least for the local impact. And then we extended that method into the future simulation. And that's where we are finding it some more interesting results. So going into the future, what we are seeing that land use change impact become insignificant. So this is for the North America. Again, this first war is the impact on the temperature, and you see almost it becomes a zero. And all other energy components are statically insignificant. Again, you do not see any stippling here, means although there are the color scale, but these results are not statically significant. So this is a question like we need some of your feedback why we do not see the impact of the land use change when we go into the future climate. This is one of the most extreme scenario that we are analyzing it here. We thought we investigated this issue in a little more detail, like we were showing you the only one point here in time. Then we took that kind of 30 years moving window and saw what is happening with respect to the temperature change. So this is a present day climate result. And as we move along the x-axis, it is like every 30 years analyzed in the future simulation. And what we find the land use change impacts in the magnitude wise, it doesn't like change significantly, but what is happening, this error bar is increasing quite significantly. And then the error bar is encompassing the zero line, and that's what it makes it insignificant. This happens both for the temperature, and this also happens for the net short wave radiation. You find that error bar is becoming quite higher. Why it is happening? What is our thought process is we looked into the climate change impact. If you think about the present day climate change, it's kind of around 0.1 degrees C per decade over the last century. So somewhat this climate change impact that is shown by the red line here were kind of a comparable magnitude that you can filter out the land use change impact. Land use change impact as shown by the black line, and climate change impact are shown by the red line. There is a scale difference. So land use change impact has been shown on a scale of -1 to +1, and the climate change impact has been shown on +10 to -10. So almost as we go into the future climate change impact becomes an order of magnitude greater than the land use change impact. And that's the reason why we think the error bar becomes so big, at least in that local methodology calculation, that the result doesn't become statically significant. So that brings me to the last slide. We do find that K13 method shows the cleaner result. In the historical climate, at least in the CMAP6, we see there is a statistically significant decrease in the temperature due to the land use change. But as we go into the future climate scenario, the uncertainty becomes quite larger, and land use change impact on temperature is not statistically significant. And our working hypothesis right now is a climate change impact has become 1 order of magnitude greater than the land use change impact, and that's why we are seeing it. Okay, with that, I'll stop.
Thank you, Sanjeev. Yeah, we have time for some questions. I can start. I wonder if it's where the land use is in the future. So, you know, the one aspect, right? Because it's a lot more coming from the tropics, and it's sort of a different signal from the tropics than from those higher latitude land use change. And, you know, it might be a cleaner, an easier signal to detect from, you know, boreal forests or croplands across the northern hemisphere, but the tropics where the signal is a bit more muted. I wonder if that could be contributing.
Yeah, that thank you, Dev. That is very good question. We are looking into like the result that I was showing you only for the North America. So we have made some boxes for the South America and the tropics, and yeah, we are looking into that issue if the signal changes. But from the spatial plot, it doesn't look like we are expecting to find any significant differences. But yeah, the differences between the tropics and how does the mid-latitude region behave, that can be a potentially a reason.
So we have a question from the chat from Suli Huo asking, in the future scenarios, did you use the transient land use data?
Yeah, we use the transient land use data. So with these simulations are coming from the LUMIP experiment. So we use SSP 585 scenario. So one thing, if I can make a point here, is we were looking for a scenario where SSP 85 has been done with the pre-industrial land use change, because SSP, yeah, that point has been noted here. SSP 585 with land use change from the 126 doesn't help much, because in that case, we do not find any difference in land use change, particularly in this mid-latitude. So that was one thing why I did not show you the direct method comparison for the future analysis.
Yeah, those simulations don't exist, unfortunately, as you know. We made the decision to try to go for this alternative land use strategy this time. We circled around that argument for a long time, but came up with this. So thanks, Sanjeev. We should move on to the final presentation, which is by Pei-Ling Wang. So Pei-Ling, go ahead on soil degradation, I think.
Yeah.
Looks good.
Okay. So thank you for having me here. I would like to update my project with Johan on human-induced soil degradation. I especially want to focus on water holding capacity, how that impact the how much water the soil can hold. So think about soil as a simple bucket. We can input water into this bucket through precipitation, and the excess water becomes surplus, and we can extract water from this bucket through actual evapotranspiration. And if the water is not enough, it becomes deficit. So today, let's imagine the bucket size is reduced by human-induced soil degradation. So with the same amount of precipitation, the surplus increases, the actual evapotranspiration decreases, and the deficit increases. So this is a very easy idea. However, most of the Earth system models don't consider soil change regardless the land use land cover change a lot. So here we want to show you our first attempt to estimate the changing soil water holding capacity, how that impact global water balance. So with just this very simple bucket model, we can see here the global actual evapotranspiration change here, and this surplus and deficit change. So you can see in areas, especially with under moist climates and with high seasonality, like here, West Africa, India, and these areas, you will see like more than 10 millimeter of water change, especially in those areas. And this model is by running soil water holding capacity under disturbed and undisturbed and human disturbed situation. So this is the difference between undisturbed and disturbed. And you can see the largest change largest decrease in water holding capacity based on our model occurred in Europe and Russia and some Indonesia. These areas didn't necessarily be the largest change in water balance because they don't have very high seasonality. So how do we get this? So to estimate soil water holding capacity, there is no direct observations or data set we can use, but we can calculate soil water holding capacity through soil organic carbon content, soil texture, sand, silt, clay content, and soil bulk density. So with these three properties, we can use soil pedal transfer functions to calculate soil water holding capacity. So in order to know the soil property change under human land use, we are trying to answer these 4 questions. So first one is how human land uses alter soil property, how environmental conditions affect soil change, and what's the vulnerability of the soil, and how the impact change with depth. So we did a lot of literature review for each soil properties. We collect published papers. Here we have 140 papers with 700 pair observations of the soil property under human land uses of agriculture, pasture, grazing, or secondary vegetation cover. And the soil state is compared with an undisturbed soil state under primary vegetation cover. And in addition to this, we also collect environmental factors such as MPP, slope, rainfall intensity, soil texture, moisture index, and moisture index range. So because we want to know the impact along depth too, so we collect all the data at different depth, and we group them in 4 land uses. And under agriculture, we further divided it into animal plowing, shifting cultivation, conventional tillage, and no-till, because those practices are very different and they often get mixed up in meta-analysis, so they couldn't see a clear trend. But here you can tell that conventional tillage and this no-till, they are very different. And for grazing, we divide into low, medium, and high intensity, and you can see it in average, their impacts are different. And for pasture, the observation is more diverse, but we can still do an average trend. And this is for secondary vegetation cover. So with this, we can define the land use impact and the impact with depth. So we built a soil degradation model for each soil property. So for soil organic carbon, sand, silt, clay, and bulk density, we create functions to predict how the soil property change based on different land use land cover types, MPP, slope, rainfall intensity, moisture index range, and clay content to represent the soil condition, and the depth factors to scale the effects. So here are the results of, we use this model to predict how soil property change and against the observations. So you can see in some properties we can do it pretty well, but for soil texture is more challenging. So now with these models and combining with the global environmental factor data set we have, we were able to model soil degradation globally based on different land use and land cover. So here are some global environmental factors. Then we have the relationship between different land use land cover on 4 different soil groups. So this is from the paper I published with Johan last year. We linked different land use land cover on 4 soil types based on the hydrological potential. So we have this condition, we assign different land use impact on the soil separately by each group. Then we finally integrate the change based on how much fraction each soil group in each grid to get a final result. So what you're seeing here is the soil organic carbon percent change due to the land use of 2015. And you can see in some areas here, the environment is more vulnerable. So you see a lot of change, although the soil carbon is not high here. And in other parts of the world, you can see, especially on the agricultural area, croplands, you can see a lot of organic carbon decrease. And these are the soil texture change, percent change. So globally, you can see 7% increase in average of 2%, and silt percent, clay percent decrease about 1%, and silt in average decrease 1%, but you can see in the wet area, silt percent is increased, and in the dry area, silt percent decreases. So this is due to water or wind erosion. For soil bulk density, you can see under almost all the land uses increase soil bulk density, especially for agriculture. And only for some grazing in some dry areas can slightly decrease soil bulk density. So combine all of the soil property change, we use pedal transfer functions to estimate water holding capacity. So this is what I showed you at the beginning. And in this condition, we assume all the annual cropland is conventional tillage and the grazing is heavy intensity. But we can also consider agriculture as no-till. If we assume all the agricultural area is no-till and grazing is light intensity, then we get the impact is reduced, or in some areas you can see soil water holding capacity increases. So this is a difference between low and high intensity. So for some areas like here, when you see a lot of water balance change, those areas, if you reduce the land use intensity, then the impact should also decrease. So this is the water balance change on the high and low intensity land use. So this is what you have seen. And when we reduce the land use intensity, you see those areas also increases actually evapotranspiration and reduce the surplus and deficit. So we did some calculation based on individual land use land cover to see different impacts of land use on water holding capacity. So in average, you can see annual cropland under conventional tillage show the largest reduce in water holding capacity. It's in average minus 14 millimeter. And if you change the same cropland to no-till, then you can reduce the impact by half. And especially if you look at different group of soil, in sandy soil, the impacts can be significantly reduced if you change from conventional tillage to no-till. But for clay soil, the impact difference is smaller than sandy soil. For pasture land use, people often think pasture is good, it increases soil organic carbon. That's true. But for other soil properties, it has negative impact. And overall, to the water holding capacity, it still can cause minus 11 millimeter of change. And grazing on the low intensity is the only land use that can increase water holding capacity in our model. And for secondary vegetation cover, you can see the secondary forest cover show higher water holding capacity reduction than non-forest. So in summary, we show conventional TAG has the largest impact on soil water holding capacity, but the change in soil water holding capacity, the impact to water balance is determined by climate mix. So only the moist climates with high seasonality are most affected by the change in soil degradation. And by showing different land use and cover impacts, we think land use management, such as rotating high and light or heavy land use, can potentially recover or improve soil water holding capacity. So the next step, we are going to include soil erosion in this scenario, because we currently only look at the soil property, but the thickness change can also largely affect soil water holding capacity too. And then we want to construct historical soil property data sets so we can estimate how soil degradation over time, how that affects the Earth system models. So, and eventually we'll want to apply in the Earth system models. So now we only do a very simple test and we can see the impact already. So thank you.
Thank you, Pei-Ling. Excellent. Well, it's really interesting work, and I'm excited to see it when we do apply it to the Earth system model, because I think it'll be some really interesting potential impacts. I think it's a huge missing piece actually in our current understanding of historical land use change. So, any questions?
Jackie has her hand up.
Yeah, thanks. That was really interesting. Can you just explain the different? I thought the grazing result was really interesting because it stood out as the only one that increased or helped with water holding capacity. But then there was difference between high intensity and low intensity.
Yeah.
So what is the difference between high intensity grazing versus low intensity grazing?
So it depends on how many livestock you put on this land. So there's I couldn't remember it here, but it's a certain amount of livestock is low in intensity, but if you put too many on land, then that, yeah.
Sure, thank you.
Dave?
Yeah, you also showed a pretty big impact from conversion of secondary land, right? And what is I missed the mechanism for that. Like, I can understand the agriculture and the grazing, that's pretty straightforward, but what's the mechanism for changing water holding capacity is conversion to secondary land?
So the secondary vegetation cover is from the literature, and it could be previously used as agricultural pasture or any kind of human land use. And although the vegetation grow back, the property usually there's a sustained effect, persistent effect of land use.
I'm going to call myself, which and I recognize you didn't. You're not including erosion yet, and maybe what the comment or question I'm going to ask only applies to the case of erosion. But it seems that the incredibly long legacy effects of changes to the soil might, are we going to have to spin up the model for thousands of years to get these long-term low intensity effects on the soil? After this is, after you've put all this in there, is it going to fully change how we think about spinning up the model?
Yeah.
Was that yes?
Yes.
Okay, good.
Can I say something about that? This is Johan.
Yeah.
Can you hear me?
Yes.
I mean, I hadn't really thought about that exact question, but obviously it has a major impact. But what we're hoping to do is that we're going to create a temporal data set basically from 850 to present, right? And so we could hopefully have a model spin up, you know, with kind of natural conditions, or a spin up with primary vegetation everywhere. And then once we know what those soil properties are, we can start to degrade them from 850 on in a transient type simulation, I think. I mean, obviously the first effort would be more of a equilibrium comparison where we just, and that would probably require 2 spin ups, I guess. But yeah, that's a bit of an issue that we haven't completely figured out yet. It's a tough one.
An important one. Will?
Yeah, I guess I wondered, could an alternative to having to do these crazy long spin-ups just be to treat soil properties the way we are now? And so that just comes off the surface data set, which is static. But couldn't you make a surface data set that's transient? And so then the soil properties you'd have to come up with what those time series look like for texture and bulk density and soil carbon. But it seems like you could get the changes in function without having to do this millennial spin up.
Yeah, I would agree with that. Sorry, Pei-Ling, you should be answering.
Okay.
Gordon, you have your hand up.
Yeah, first, Johan, let me say to you, Johan, it's great to hear your voice. I didn't realize you were on. So it's really good to hear you. I hope everything's going well for you.
Yeah, it's going pretty well.
Yeah.
Thank you.
And then this is for both Johan and Charlie. You know, I think this question of Charlie, your point about spin up is really interesting. And you were talking about it in terms of soil properties, but even in terms of vegetation, why do we expect that at 1850 or even 1750 or even earlier, this idea that vegetation was in equilibrium is just crazy. And so, I wonder if we just, what I would say about the soil dynamics spin up is I think it's it's not just that, it's part of a bigger issue of like, well, how do we actually initialize our models? And we have this concept that at some point in time, the biosphere was in equilibrium with climate. And, that's not really what's going on. So I think that's just a bigger topic, to think about at some point.
Mm-hmm. Thank you.
Yeah. So Gordon, what we're doing for these fire emissions runs, prognostic fire emissions that are being used by the atmosphere. What we are finding is that if you spin up in 1850 and then all of a sudden go into a transient, there's this huge pulse of emissions that comes from all of a sudden you're doing land use change and all the fires that come from that. And so it totally screws it up because then the radiative forcing it's like a pulse function of the radiative forcing, and there's this big decrease in cooling that happens right at the beginning. So what we're doing is we are trying to at least starting to address this by starting in the year 1750, coming to equilibrium, but then allowing 100 years of land only, in the fully coupled model, but allowing the land use change to occur to kind of like come into quasi-equilibrium with the climate before the real thing happens in 1850 where you start changing everything. So it definitely makes the whole spin up more complicated. So just so you know, a little bit trying to baby steps into that minefield.
So Donica has a question and a comment in the chat. One she'd love to talk about connecting the tillage code with the soil water holding capacity stuff. And then also question, do forest versus grasses change the water holding capacity due to rooting depth?
So in this study, we estimate change to up to 1 meter. And because deeper than 1 meter, we don't see much change. So we calculate the change for each soil layer. We have 7 layers. then we integrate the change to the depth of soil. So that's different. It's not 2 meters, but up to 2 meters of soil. Yeah, based on the soil depth. So we do have a deeper, we do improve and include the rooting depth.
In a sense, it's included because what we've done is we're looking at, you can think of this as an equilibrium experiment in a way, over say a 50-year period where you have one vegetation type and then you transition to another. And we're looking at how the properties of the soil change through all the depth layers, well, through 1 meter, because there's just no data below that. And then sort of applying those. So it's implied that there's, you know, when you switch from PFT tree type A to whatever, grassland or cropland, it would imply that these are trees that are, you know, involved in that process.
Okay, yeah, I was just surprised by the fact that, you know, secondary forest had a much more reduced water holding capacity than secondary grassland, for example.
Yeah, I think it's because the soil's not disturbed as much. There's no plowing involved with the secondary. Pei Ling?
And usually on the secondary vegetation cover, it's the soil is better and the environmental is better for agriculture or pasture, any land uses. So usually the land use intensity is higher than those on the non-forest cover.
Okay, thank you.
It also raises a question of where we do what we do, right? You know, humans pick the best soil for agriculture typically. We don't choose to go on the worst soil patch that we can find. So I think this is why the first paper we did was kind of critical to thinking about what soils do you choose to work on. And I think even an experiment that would just look at, say, putting agriculture on a better soil type within a column would be a very interesting experiment, as opposed to some average soil type, and agriculture is equally represented across that average. Putting it on clay versus on sand makes a huge difference in terms of the whole atmosphere, or soil atmosphere moisture exchange and energy. At least that's my thinking, but you know, I've been known to be wrong before.
Other questions?
Will, I'll let you take over if you want for to close this.
Yeah. I guess more broadly, there's only 5 or 10 minutes left before we're scheduled to adjourn. But I wonder if folks have, you know, heard a bunch of fates talks and a bunch of land use change talks and a bunch of hydrology kind of talks today. So it's a lot to try to digest. You know, just over lunch, I was like, man, there's such cool science that people are doing, and I wish we got to hear more about it more often. So I appreciate all the effort that folks put into their presentations. It's much appreciated. But at this point, it's just kind of open discussion if folks have other thoughts or things they've been thinking about throughout the day. The Zoom bomb might have dropped. Oh, you just took out some energy. Good.
Hey, yeah, I can take over. Actually, I have a question. I have a question regarding to the fate simulation, especially of the fire, because we know we can actually use the fire data from the GFED to try to simulate the historical fires and emissions, but actually, especially in the Amazon, there's many evidence showing that probably the deforestation, commodity deforestation could be the main driver to the fire events there. So which will brings very huge challenge for us to predict the land use emission and also the fire emissions in the future, because sometimes it is kind of like unpredictable. I don't know. What do you think? How, especially this question for Jackie and for Charlie, what do you think about these issues? How can we like further go further to improve this? Yeah, thank you.
I guess I'll start. I mean, so the FATES has an active logging module, and so FATES has an active logging module, and then Charlie has been working closely on incorporating land-covered land use change, but linking those pieces with fire has yet to be done. And so your point about the importance of deforestation as a driver of change in the Amazon is an essential component. And so with the fire simulations that I'm doing, it's really looking at, can we capture the fire regime? And so that feedback, that long-term feedback between climate, vegetation, and ignitions, just at a basic level. But then the addition of humans and the problems that you get, or the additional complexities that you get with anthropogenic ignitions, deforestation, clearing, that's another component. And so I think I'm looking at this as sort of a starting point, and then we add in the land-covered land use change. But yeah, it's definitely an essential piece that we bring them both together.
And Jackie, of course, we can start with what Phong has done for degradation fires.
Yeah, that's what I was going to say, just in addition to what Jackie said. I mean, the CLM already has so much information about fugitive fires and all these other things, and we need to put in the linkages and then go from there.
But I thought your presentation on deforestation, the work that you're doing with Jim Randerson, it's a compelling motivation to really get at what's happening with this forest loss, for the feedbacks within the system.
Yeah, and also we have just discussed yesterday in our group meeting. There's recent paper using the satellite data trying to map the global forest carbon fluxes. Yeah, actually there's some like needs on the very fine spatial scale quantification, because typically some previous satellite data cannot capture like some small scale fires, which is typically smaller than 6.25 hectares small fire. But now as they have trying to include these like very fine scale spatial resolution fire events, and their quantification is typically, I think it's pretty large than the previous method, trying to quantify the carbon emissions from the land use change. So that is, I think maybe, yeah, especially in the future phase could consider like trying to apply all the strengths from this very high spatial resolution satellite data, trying to improve that. Yeah, just a thought.
Yeah, that's good to hear. And I'll get in touch with you about that data set. And so I should mention that I'm not tuning the FATES model to GFED. And so the behavior of the burned area and the vegetation it's emergent from the model through the interactions of climate and fire. And so I'm not doing any tuning to actually force it to track GFED. But these small fires are an issue, because so within FATES, if a fire happens based on an energy threshold, we track it. And so like there is a disconnect, and these small fires, because South America generally has low intensity small fires, or more of them. It also has very gigantic fires, but the disconnect between whether or not you can see these fires from satellite observations is an important point. And so looking at another data set that includes that, or incorporating that, would be good. So yeah, it'd be great if you could send me that reference, or I'll get in touch with you.
I explained that paper is not like kind of like currently I think the best data is still GFED, and that paper is based on like a 30 meters scale above ground biomass. So they claim that this above ground biomass map could capture the small scale emissions. Yeah. So but anyway, for that for Wi-Fi emissions, they have used like emission factor map, which is based on 1 kilometer spatial Wi-Fi map. So which is cannot capture the small scale fires. But yeah, they claim that the biomass could do this.
Well, and emission factors themselves it's a broad scale biome level combustion. And so there are issues with that as well. But yeah,
Right.
yeah,
Right.
we should stay in touch about that for
Yeah.
sure.
Yeah.
Will, do I have time to ask a fire question?
Yeah.
And I guess this is to Jackie, but maybe it's more general. You know, not only are we simulating a world right now, a world without fire management, but we're also sort of simulating a world without grazers, right? And to the extent that grazers consume, you know, a large fraction of the burnable fuel on the planet, do we need to? I mean, is that like how important is that in the overall scheme of things to include? Do you think?
I think grazing as an impact on fuel availability is important for large parts of the world, particularly like Africa, large parts of Africa. And so areas that have high burning. So yeah, and yeah, I haven't thought about that as a management technique. So yeah.
Julia Pongratz thinks it's quite important.
I agree.
They've included it into their model. I'm trying to convince both the University of Wyoming and CSU to help us on projects to do grazing. So if I have any luck, then maybe we'll have somebody to work on it.
Adriana?
Oh yeah, I was just going to say that, yeah, I think we've seen recent papers that show that, you know, putting animals into is like a major thing that needs to happen in the carbon budget for the Earth system, and like grazing, and you know, we've seen in just a small example, like in Yellowstone with the reintroduction of wolves as a predator has changed the vegetation type, and so I think it's really important.
Well, okay, sorry, I forgot to raise my hand. It's been a long day. But I think management of all kinds is an essential part of the discussion with fire. And so, yeah. And so management in terms of grass is an important component. And I think that is very important globally. But then if we think more locally here in the United States, fire management and its connection to wildland urban interface is an essential piece that we need to move forward. And so, and it's much easier to do that with a size structured model. So yeah, well, not easy, but possible.
Great. Well, we're scheduled to come back at 9 tomorrow. So look forward to another round of good talks, and thanks everyone who presented today. See you all tomorrow.
Thanks, everybody.
Yep.
Tomorrow.
That was
Thanks,
good.
Elizabeth.
Another good day. Everything went so smooth.
I know, it was buttery. You're like a pro at this. I liked it when I was like, oh, I'll put a poll up, and then all of a sudden there was a poll up. That's nice.
Yeah. Oh, my stuff. Okay, move along. We're still doing algebra.
Still working on algebra. Yeah.
Yeah.
Hi there.
Hi.
Seriously. Yeah. So, and we had really high numbers again today too. What's today? 64 this morning, 50,
yeah.
a high of 58 this afternoon.
That's great. Good. Yeah, so I guess no changes for tomorrow. Like Donica I looked back at the wrong email when I said that it was Donica today, so it's Donica tomorrow, and me
Okay.
monitoring the chat. And they have for the coffee break, let's do the same thing, just let people choose their own adventure. Did you have folks that couldn't join a room who wanted to?
Only Charlie said he needed help, but he's like, oh,
Okay.
just send me off to room number 1. So I did, and that was no problem.
Okay.
So we had, I think one room maybe only had 2 or 3 people, and then 2 rooms had like seven or eight.
Bigger group, yeah.
Yeah. Yeah, so I'll just make fewer rooms tomorrow. I really didn't know how that was going to break out.
Yeah, I was surprised, but roughly half the people were just like, no, I'm not, I'm not going to go, which is fine.
Yeah, especially for people that, it's like, mid to morning or late afternoon by the time we start. It's already such a long day.
I probably go out to get dinner.
Yeah.
Yeah.
That just makes it hard, so.
Yeah, 2 of our presenters tomorrow are actually in China.
Okay.
So I have no idea what time of day it'll be for them. I'm sure it won't be sane. And I think you've gotten at least one of their presentations. They're both in the morning. So anyway, I hope they both are able to make it and present. Yeah. We'll see.
Yeah.
That's the only hiccup that we have that I know of potentially.
No, that should be fine. Yeah, and I'm glad that they can, because we did have some issues with Paleo. Esther gave some of her people the option of recording their talk and sending us the recording.
Oh.
And so then she was playing the recording for them the one day, and then her internet was wonky. And then I know what it was too. Then her laptop fan kicked in, and so the noise
couldn't hear anything.
Was really bad. So then the next day she had one of her teammates who actually had permission to be at Mesa. He presented, and then that worked out better. But I'm like, it's a good option, but it also makes things a little bit difficult.
Yeah. You're not going into Mesa at all?
No, I first asked about permission to go in this month to run working groups.
Yeah.
But then they were really coming down on, like, if you've asked for permission and then you don't go in, you have to go through this, like, let them know every day. And my kids doing school at home and the weather's so unpredictable. I'm like, I don't want to take that away from someone else. So I'm like, I'm gonna tough it out. So I mean, it's not like I'm presenting the whole time. That would be a different story. I'm just behind the scenes.
Yeah.
Great. All right. So last day tomorrow. It's pretty exciting.
Thanks for your help. Yeah. You can celebrate after that.
Yeah. All right. Have a